Having examined Earth's habitability and life in this documentary series, we now focus on the quest for extraterrestrial life inside our solar system. Numerous locations are available for exploration, including other planets, their moons, and thousands of known asteroids and comets. Consequently, a plan is required to concentrate our efforts on the most probable livable worlds. The initial phase of this technique involves identifying appropriate areas for investigation. Thus, we commence this chapter by examining the environmental prerequisites anticipated for life in any given world. Considering those criteria, we will conduct a biological exploration of the solar system to identify potential locations for fulfillment. This will allow us to determine which worlds warrant the most significant focus in our research and the experiments presented. In our solar system, our primary focus is on the search for microorganisms or other forms of basic life. We have acquired sufficient knowledge to confidently assert that no other advanced civilization has ever emerged in our solar system. Discovering any form of life would significantly enhance our comprehension of biology and provoke serious philosophical reflections on our position within the universe. Whether we find life in our solar system or not, the search will teach us a lot about the conditions that make planets habitable, which will help us learn more about other planetary systems. There is no location comparable to home within our solar system. No planet other than Earth possesses a breathable atmosphere or enough surface water suitable for consumption. There is no other planet with a combination of surface temperature and pressure that would allow human survival without a spacesuit. Few celestial bodies possess atmospheres that shield them from harmful UV radiation from the sun or high-energy particles from outer space. Without doing a lot of engineering work to build habitats that can support themselves or terraform a planet to change its basic conditions, we cannot survive on anybody in our solar system for a long time. When discussing habitability, we typically refer to an environment capable of sustaining any form of life, not exclusively human life. This significantly expands the possibilities. Life flourished. However, we could not have endured on our planet throughout its existence. Life on Earth, both past and present, has flourished in a significantly broader range of circumstances than we can withstand. Upon identifying potentially habitable worlds within our solar system, it is imperative to delineate the spectrum of circumstances deemed suitable for life. We have addressed several of these concepts in earlier chapters. We will consolidate all elements into a coherent list of environmental prerequisites for life. Where are the components of life likely to be found? The fundamental prerequisite for life is a collection of chemical ingredients necessary for constructing cellular components. Life on Earth utilizes approximately 25 of the 92 naturally occurring chemical elements, with only 4 elements: oxygen, carbon, hydrogen, and nitrogen, constituting over 96% of the mass of living beings. Therefore, a primary requirement may be the existence of most components life utilizes. Virtually everyone globally can fulfill this criterion. Stars generate all chemical elements and save hydrogen and helium. Although less common than hydrogen and helium, these heavy elements are pervasive. Furthermore, oxygen, carbon, and nitrogen, arguably the most essential elements for life, rank as the 3rd, 4th, and 6th most plentiful elements in the cosmos respectively. The proportions of heavy elements differ. They constitute around 2% of the chemical mass of our solar system, although less than 0.1% in certain ancient star systems. Nonetheless, every star system we have examined contains a minimum quantity of all essential elements for life. The process of solar system creation provides more justification for anticipating the prevalence of life's ingredients in other celestial bodies. According to the nebula theory of solar system creation, planets formed as solid particles condensed from gas in the solar nebula, then accreting into planetesimals and finally into planets, moons, asteroids. Condensation is the initial phase of this process, influencing only heavier elements or hydrogen compounds containing heavy elements. This is because pure hydrogen and helium exist exclusively as gases. Provided condensation and accretion transpire, we anticipate that the resultant worlds will include the requisite components for life. It is important to recognize that this fundamental reasoning remains unchanged, even when considering forms of life that differ significantly from terrestrial life. Life on Earth is carbon-based. There is substantial justification to believe that life elsewhere would similarly be carbon-based. Nonetheless, we cannot dismiss the potential for life based on another chemical foundation. Life forms that depend on a different element use a different mix of elements or different proportions of those elements than carbon-based life on Earth. Nevertheless, stars continue to generate components that ought to be ubiquitous. Regardless of the type of life we pursue, we are certain to discover the essential components on nearly every planet, moon, asteroid, and comet. A more stringent criterion is that these components must be present in molecules that can serve as preformed building blocks for life. Initially, the Earth likely possessed many amino acids and other intricate chemicals. It is believed that Earth's organic molecules originated from three sources: atmospheric chemical processes, reactions near deep-sea hydrothermal vents, and extraterrestrial materials delivered to Earth. The initial two sources can exist solely on planets with atmospheres or oceans. Nonetheless, the third source should have disseminated analogous chemicals to virtually all celestial bodies within our solar system. Research on meteorites and comets indicates that organic compounds are prevalent in asteroids and comets. Asteroids and comets hit every celestial body when they first formed, so each world probably had a small amount of organic molecules. Interplanetary dust may have also contained organic compounds that settled on newly formed worlds. Nonetheless, solar radiation typically degrades organic compounds on surfaces lacking atmospheric protection. These molecules may remain intact beneath the surface, as observed on asteroids and comets, but they may not react unless influenced by a liquid or gas. We should start searching places where organic molecules will likely be involved in chemical processes. We should focus on planets with an atmosphere, a surface, or a liquid medium below the surface, like water. Where might we anticipate discovering energy essential for life? Life necessitates an energy source to drive metabolism and supply molecular building components, section 5.3. Remember that life on Earth utilizes a diverse array of energy sources. Certain organisms derive energy directly from sunlight via photosynthesis. Some species obtain energy by ingesting organic molecules, such as those from photosynthetic organisms, or by chemical reactions involving inorganic chemicals like iron, sulfur, or hydrogen. Sunlight is ubiquitous throughout our solar system, although its intensity diminishes somewhat with greater distance from the sun. The energy emitted by sunlight diminishes with the square of the distance from the sun. For instance, if a leaf of a specific size were placed on a planet located twice as far from the sun as Earth, it would absorb merely 1/4 of the energy that the same leaf would get on Earth during the same duration. At 10 times Earth's distance from the sun, approximately the distance of Saturn, photosynthetic organisms on such a planet would need to be much bigger than Earth to have a larger surface area to absorb light, be better at collecting energy from the sun, or have a much slower metabolism and reproduction rate. In the distant outer solar system, sunlight is nearly insufficient to sustain life. Chemical energy sources impose limitations on life. Various circumstances can initiate chemical reactions, but they only occur when potential reactants come into contact. This suggests that the continuous reactions required for life energy can only occur in environments where elements constantly interact. In practice, this means that there needs to be either an atmosphere for mixing gases or a liquid medium for mixing materials on or below the surface of a planet. These are the same conditions needed to get life's basic building blocks. Is liquid water essential for life? Alongside organic building blocks and energy, liquid water is indispensable for all life on Earth. Water fulfills at least three crucial functions for life. It dissolves organic molecules, rendering them accessible for cellular chemical reactions. It facilitates the transport of chemicals into and out of cells, and it is directly involved in numerous metabolic reactions occurring within cells. Envisioning existence devoid of a liquid medium, fulfilling these functions is challenging. Can a liquid other than water perform these functions? The potential for other liquids to sustain life without liquid water remains uncertain. However, many limits warrant consideration. A substance that could serve the functions of water must, akin to water, be relatively abundant. On Earth, the sole liquid, other than water, that is frequently encountered is molten rock, which is so intensely heated that it is challenging to conceive of life enduring within it. Nevertheless, other prevalent compounds may exist in liquid form on frigid celestial bodies. We present the freezing and boiling temperatures at 1 atmosphere of pressure for prevalent chemicals that may exist in liquid form within our solar system. The final column indicates the width of the liquid range, determined by subtracting the freezing point from the boiling point. While we cannot exclude the other liquids, water possesses at least three characteristics that render it significantly more appropriate as a liquid medium for life. Initially, as illustrated in the table, water maintains its liquid state across a broader and elevated temperature range. The liquid range of ethane is similarly extensive, albeit at far lower temperatures. A broader range increases the likelihood that the chemical remains liquid during weather or environmental fluctuations. An elevated temperature range enhances chemical reactions. Chemical reactions typically occur more swiftly at elevated temperatures due to the increased molecular motion. The rate of a specific chemical reaction generally doubles with every 10 degrees Celsius rise in temperature. Consequently, chemical reactions in water typically accelerate significantly more than analogous processes in liquid ammonia, methane, or ethane. Life utilizing these alternative liquids would likely exhibit a significantly slower metabolism than life on Earth. The diminished reaction rate may render the emergence of life in these alternative liquids less probable, as its creation likely necessitates numerous intricate chemical processes. The second benefit of liquid water pertains to a peculiarity in the freezing process of water. Most substances exhibit greater density in their solid state than their liquid state. Nevertheless, water is an anomalous case. Ice possesses a lower density than liquid water, resulting in buoyancy. No other liquid possesses this characteristic alongside water. This trait facilitates the sustenance of life on Earth. During winter, when surface temperatures drop sufficiently for water to freeze, a floating ice coating develops on lakes and seas. This ice covering insulates the underlying water, enabling it to remain liquid and sustain life. The buoyancy of solid ice may be more crucial for long-term climate stability. During intervals of Earth's cooling, such as the ice ages, reduced temperatures facilitate increased ice formation on the surface. If this ice were to sink, the surface would remain covered with liquid water, then freeze and submerge. The process would continue until all liquid water at the surface evaporated, leading to entirely frozen lakes and oceans. Consequently, due to the buoyancy of ice, a cool period enhances the thickness of the insulating ice layer on lakes and oceans, thereby reducing the likelihood of full freezing. The third benefit of liquid water compared to other liquids is the electrical charge distribution inside its molecules. In individual water molecules, the electrons are dispersed, so that one side acquires a net positive charge, while the opposite obtains a negative charge. Molecules exhibiting this type of charge separation are called polar molecules. Polar originates from the concentration of positive and negative charges at opposing ends, or poles, of a molecule's axis. It is unrelated to temperature. This charge separation influences the solubility of other compounds in water. Charged molecules and salts readily dissolve in water. Molecules without charge separation, like oil molecules, are insoluble in water. The charge separation feature of water is essential for life on Earth. Living cells possess membranes impermeable to water, thereby safeguarding the internal contents of the cells. When living cells are immersed in liquid ethane, methane, or ammonia, substances exhibiting lower charge separation than water, their membranes typically disintegrate. Charge separation facilitates the formation of a certain sort of chemical connection known as a hydrogen bond, which is crucial to the biochemistry of life on Earth. The formation of hydrogen bonds during the freezing process of water explains the reduced density of ice, which accounts for its buoyancy, as these bonds force the molecules into a slightly expanded configuration. Our research indicates that water surpasses other liquids for sustaining life in 3 respects. 1. It remains in a liquid state across a broader and elevated temperature spectrum. 2. Solid water exhibits buoyancy. And 3. The dipole moment of water molecules facilitates chemical bonds unattainable with alternative liquids. These advantages confirm the necessity of liquid water as a foundation for life. However, the argument remains inconclusive. Negating the third advantage is a viable option. If extraterrestrial life possessed cell membranes composed of molecules with distinct charge separation characteristics, they could dissolve in water but remain insoluble in ammonia, methane, or ethane. We are uncertain of its feasibility, yet we cannot dismiss it. We currently lack sufficient knowledge to determine the potential for life in liquid mediums other than water. Nonetheless, due to the established benefits of water and the prevalence of liquid water in the solar system compared to other liquids, the pursuit of liquid water is a prudent initial approach in the quest for life. What are the environmental prerequisites for habitability? This part commenced with an enumeration of the environmental prerequisites for life, which will assist in determining which celestial bodies to prioritize in our quest for potential life habitats inside our solar system. In general, we have determined that the environment must fulfill 3 primary criteria. 1. It requires a source of chemicals to construct living cells. 2. It requires an energy source to sustain metabolism. 3. A liquid medium, most probably liquid water, is essential for the transfer of life's molecules. Nearly all worlds satisfy the initial criterion. The second criterion is more restrictive. Nonetheless, numerous worlds should still possess adequate sunlight or chemical energy to support life. The third requirement, a liquid, is the most rigorous. Furthermore, any global assembly fulfilling this third criterion will likely satisfy the initial 2. A liquid such as water can promote chemical reactions with inorganic planetary substances, providing a possible energy source for life, which is indeed utilized by several bacteria on Earth. Consequently, according to our present comprehension of life, we may distill the criteria into a singular litmus test for habitability. A planet can be deemed livable if it possesses a liquid medium, most likely liquid water, though it may encompass other liquids. The necessity for a liquid significantly constrains the potential for life in our solar system, though not as severely as one might initially assume. Different ecosystems on Earth, like the deep ocean and rocks below the surface, contain liquid water and living things. This shows that liquid water must only be present in some form for an area to be habitable, not just on the surface. A significant proportion of the celestial bodies in our solar system have likely satisfied this requirement at some point in the past, and many continue to do so. Remember that all our knowledge of life is derived from examining existence in a singular realm, our own. As a result, our habitability assessments may be based on an overly limited view of life, which means that our criteria for assessment are also very limited. Science fiction authors have envisioned peculiar living forms in environments vastly different from those we have examined here. Nature may exhibit even greater ingenuity. The quest for life must begin, and it makes sense to start by examining the conditions that could sustain life as we understand it. Should our preliminary investigation prove overly restrictive, we can broaden our scope. Envision residing a century hence, when we have dispatched orbiters and landers to every significant celestial body in our solar system, and when humanity may potentially inhabit and operate on extraterrestrial worlds. At that point, a course on life in the universe could start with a real biological exploration of the solar system. This would help us determine which celestial bodies are home to life and why. We are unable to do a comprehensive biological tour today. Nevertheless, we possess sufficient knowledge to hypothesize which worlds will most likely be livable. This section will concentrate on our neighboring celestial bodies in the inner solar system. The Moon and the terrestrial planets, Mercury, Venus, and Mars. Is the existence of life conceivable on the Moon or Mercury? Despite Mercury being a planet and the Moon orbiting Earth, both celestial bodies exhibit several similarities. Both are riddled with craters, figure 7.5. Both are far smaller than Earth, so diminutive that they have dissipated most of their internal heat, resulting in the absence of continuous volcanism and negligible tectonic activity. The absence of volcanism results in no outgassing to introduce gases into the atmosphere, and their diminutive sizes lead to insufficient gravity, which has long permitted any former atmospheric gases to dissipate into space. Consequently, both realms are fundamentally devoid of air. Mercury and the Moon are distinguished as two of the least livable locations in the solar system, mostly due to the absence of liquid water on either celestial body. The Moon has minimal water content, which is logical considering its formation, which resulted from a colossal impact. Scientists have long hypothesized that water ice may be concealed under the bases of polar craters, where it might have accumulated over millennia from comet impacts and stayed frozen due to constant shade. This hunch was validated in 2009 when the rocket from NASA's LCROSS probe impacted a crater near the South Pole, ejecting ice-laden debris. Subsequently, a radar sensor on India's Chandrayaan-1 spacecraft identified indications of no less than 600 million tons of water ice in craters next to the Moon's North Pole. Surprisingly, more missions found small amounts of water mixed in with the top layer of lunar regolith over large parts of the Moon's surface. We have yet to discover the source of this water. Nonetheless, although this water ice may be advantageous for prospective human settlers, it does not provide a liquid habitat for life. Mercury. Mercury may possess chemically bound water within its surface rock from its origin. Nonetheless, it is improbable that any water exists in liquid form. Mercury's rotation period of 58.6 days and its orbital period of 87.9 days result in days and nights lasting around 3 Earth months apiece. Daytime temperatures attain 425 degrees Celsius, excessively high for liquid water. The absence of an atmosphere results in nighttime temperatures descending to -150 degrees Celsius, which is excessively frigid for liquid water to exist. Mercury may harbor ice in the depths of its polar craters. Nonetheless, this enduring ice seems improbable as a viable habitat for life. Although the Moon and Mercury appear to be unlikely candidates for the existence of life, They can provide significant insights into the formation and history of our solar system, elucidating the reasons behind the habitability of certain worlds and the inhospitality of others. Consequently, both realms are subjects of continuous investigation. Scientists are particularly keen to acquire further knowledge about Mercury after the Messenger spacecraft commences its orbit around the planet, an event anticipated to have transpired. Is it possible for life to exist on Venus or Mars? Future or current life prospects appear significantly more favorable when considering our closest planetary neighbors, Venus and Mars. Venus is called our sister planet, due to its proximity to Earth and nearly equal size. Mars is significantly smaller than Earth. Nonetheless, images captured by spacecraft depict a strikingly Earth-like terrain. Both planets possess the potential for sustaining past and contemporary life. However, Mars appears significantly more viable. Venus. Dense clouds completely obscure Venus, figure 7.7, leaving previous generations of astronomers to only speculate about its surface conditions. Certainly, that did not inhibit conjecture. Basic calculations on Venus's proximity to the Sun, around 2/3 of Earth's distance, indicate that if Venus possessed an Earth-like atmosphere, its global average temperature would be approximately 35 degrees Celsius, 95 degrees Fahrenheit. This reality prompted previous generations of science fiction authors to envision Venus as a verdant tropical utopia. The actuality is markedly distinct. The surface temperature of Venus reaches an astonishing 470 degrees Celsius, about 880 degrees Fahrenheit, sufficient to liquefy lead. This severe temperature endures globally, both during the day and at night. A dense atmosphere exerts a pressure 90 times greater than that at Earth's surface, comparable to the pressure seen at a depth of approximately 1 kilometer, 0.6 miles, in the oceans. In addition to extreme pressure and high temperatures, Venus's atmosphere includes sulfuric acid and other deadly substances. The Soviet Union dispatched landers to Venus which transmitted data only briefly before being incapacitated by extreme temperatures. Unlike being an aesthetically pleasing sister planet to Earth, Venus resembles a conventional depiction of hell. What are the factors that contribute to the harsh conditions on Venus? The greenhouse effect explains why our planet is hospitable. Remember that the greenhouse effect prevents Earth from becoming entirely frozen. The Earth's habitability is due to a moderate greenhouse effect that retains sufficient heat to elevate temperatures over the freezing point of water. The greenhouse effect functions similarly to Venus, albeit somewhat more so. The intense greenhouse effect on Venus, frequently referred to as a runaway greenhouse effect, is predominantly due to the presence of carbon dioxide in its atmosphere. The Earth experiences a moderate greenhouse effect, due to carbon dioxide constituting less than 1% of the atmosphere. Conversely, carbon dioxide constitutes over 96% of the significantly denser atmosphere of Venus. We can elucidate this disparity in atmospheric carbon dioxide by comparing the behavior of carbon dioxide gas on each planet. Both planets have emitted comparable total quantities of carbon dioxide across their lifetimes. Nonetheless, although nearly all carbon dioxide emitted on Earth is currently sequestered in carbonate rocks or dissolved in the oceans, 170,000 times more than in our atmosphere. All of Venus's emitted carbon dioxide persists in its atmosphere. Consequently, Venus's elevated temperature is attributable to the potent greenhouse effect of its atmospheric carbon dioxide, while the high pressure is due to the substantial concentration of this gas. The excessive surface temperature effectively precludes the possibility of life on Venus's surface now. The temperature is excessively high for liquid water, much less for liquid ammonia, methane, or ethane. Nonetheless, the surface may have been conducive to habitation in the past. Carbon dioxide is sequestered in Earth's carbonate rocks via the carbon dioxide cycle. This cycle relies on plate tectonics and seas. Carbon dioxide dissolves in the oceans, undergoing chemical reactions to produce carbonate minerals. Venus lacks a comparable cycle due to the absence of oceans and plate tectonics, as well as the lack of a mechanism for atmospheric carbon dioxide removal. However, the circumstances may have been markedly different in the remote past. The Sun's significantly lower luminosity in its early history may have permitted the existence of oceans on Venus some 4 billion years ago. If Earth-like refers to contemporary Earth conditions, it is plausible that ancient Venus may have exhibited more Earth-like characteristics than Earth did during that period. If a specific location on Venus exists, microorganisms may continue within the clouds. At approximately 50 kilometers above the surface, the greenhouse effect significantly diminishes, allowing for the presence of liquid water droplets. Even though the clouds are very acidic, their sulfur may help chemical reactions that can provide enough energy for extremophiles that have evolved to live in this environment. Unless we discover life in the clouds of Venus, which is improbable, we may never ascertain whether Venus harbored life in the remote past. Crater counts indicate that Venus's surface is under 1 billion years old, implying that volcanic or tectonic activities have altered or covered older rock formations. Consequently, if life had originated and persisted until the catastrophic greenhouse effect rendered Venus inhospitable, all fossil evidence would have been obliterated long ago. Mars. While Venus experienced excessive heating early in its development, Mars had a contrasting cooling process. Mars undoubtedly possessed flowing water and a denser, warmer atmosphere. Nevertheless, some 3 billion years ago, climate change led to the planet effectively freezing over. All residual surface water has frozen, and Mars has lost significant atmospheric gas, resulting in insufficient surface pressure for liquid water to exist. Nonetheless, historical water renders Mars a leading contender for a former life. Furthermore, Mars possesses sufficient internal heat to sustain liquid water beneath, suggesting that life may exist. Mars is a promising candidate for past or present life. Should it be determined that life never existed there, we may need to re-evaluate our assumptions on the probability of life emerging under optimal conditions. Due to Mars's significant potential for habitability and life, we will postpone its consideration. Beyond Mars, the diminishing intensity of sunlight renders surface life progressively improbable. Numerous worlds possess internal heat that may sustain liquid water and supply energy for life. In this section, we will embark on a biological exploration of the outer regions of our solar system. What are the possibilities for life on Jovian planets? The 4 Jovian planets, Jupiter, Saturn, Uranus, and Neptune, exhibit significant differences from the terrestrial planets. They possess significantly greater mass and reduced density and predominantly comprise hydrogen, helium, and hydrogen compounds, such as water, methane, and ammonia. The Jovian planets differ from the terrestrial planets in their internal architecture, as inferred by scientists from observations and theoretical models on the behavior of their materials, considering their masses and diameters. These planets do not possess a solid surface akin to that of Earth. Their outer layers are made up of clouds that can be seen encircling thick layers of gaseous hydrogen that are mixed with helium and hydrogen compounds. Within their innards, enormous pressure compresses hydrogen into a liquid state, and in Jupiter and Saturn, the pressure escalates to a level where hydrogen becomes a metallic form. Each possesses a core composed of rock, metal, and hydrogen compounds in their centers. Yet the pressure is so immense that these materials exist in a phase unlike any observed on Earth. If observable clouds of gaseous, liquid, or metallic hydrogen descended upon any of these planets, you would descend until the escalating pressure ultimately crushed you. Ultimately, your remnants would submerge in a heated expanse of unfamiliar liquids. The considerable distance of these planets from the Sun results in exceedingly low temperatures in their upper atmospheres. Nevertheless, observations indicate they must all possess elevated temperatures in their deep innards. This heat cannot drive geological activity, as these celestial bodies lack solid surfaces akin to terrestrial ones. Nonetheless, the heat guarantees their atmospheres maintain sufficient warmth for liquid water at certain altitudes. Furthermore, chemical reactions driven by the frequent lightning detected in their atmospheres may supply energy for life. Is it plausible to envision life here? Jupiter and Saturn. First, we shall examine Jupiter, the largest of the 4 Jovian planets. Saturn's internal structure is sufficiently analogous that identical considerations should apply. Jupiter's temperature is far below freezing at its cloud tops, but increases rapidly with depth. Jupiter possesses several cloud layers, each created by the condensation of various gas types. Clouds composed of liquid water droplets can develop at a depth exceeding 100 kilometers within Jupiter's atmosphere, representing slightly more than 1% of the distance between the uppermost clouds and the core. Considering the favorable temperature and availability of liquid water, one can speculate whether Jupiter could support life at this atmospheric depth. Let's discuss the movie 2001, A Space Odyssey, for a moment. In A Space Odyssey, 5 well-groomed astronauts and a scheming computer named HAL are en route to Jupiter. Indeed, we acknowledge that this event did not occur, and 2001 is now considered a distant past. This Stanley Kubrick epic remains a cinematic masterpiece, including music and scenes that continue to influence popular culture and pioneering visual effects since its release in 1968. If you have not yet viewed it, you ought to do so. What is the purpose of astronauts and a rogue computer traveling to this colossal planet? Is it to examine Jupiter's intricate, turbulent atmosphere? No, it is incorrect. Are they undertaking a trip to investigate the formidable magnetic field of the massive planet? Nevertheless, the response is negative. They may be seeking evidence of primitive life on the moons Europa, Callisto, and Ganymede, all of which potentially harbor concealed oceans beneath their icy surfaces. In fact, that is not correct either. These Jovian astronauts are en route to the largest planet in the solar system due to interference from an unidentified extraterrestrial species. 4 million years ago, certain benevolent extraterrestrials observed Earth and concluded that the planet's primate population had potential. Upon contact with the local monkeys, they erected a dark grey monolith that transformed the simian population from a group of howling imbeciles into tool-using primates. This is an extraordinary narrative that, if authentic, would perplex all paleontologists. Nevertheless, the extraterrestrials were dissatisfied with merely a second monolith on the moon, safeguarding the possibility that an intelligent race could eventually advance technologically enough to depart its planet and discover this peculiar relic. The lunar monolith subsequently guided us to Jupiter. Thus, the interplanetary spacecraft Discovery 1 is en route to the largest planet in the solar system. The aspiration appears to be that by traveling to this colossal planet, Homo sapiens can ultimately uncover the significant secrets these benevolent extraterrestrials intend to impart. 2001 is equally a space anomaly, as it is a space journey. Disregard the notion that the message discovered at Jupiter primarily constitutes a perplexing psychedelic light display. Disregard that the ship's eloquent onboard computer is more cunning than Machiavelli. Ultimately, the most troubling aspect of 2001, apart from the disappointing reality that our actual space program remains far from launching human crewed flights to Jupiter, is the notion that our history and future are merely the subjects of an extraterrestrial science experiment. We are really a collection of orchestrated marionettes. In the future, we will explore numerous celestial bodies inside our solar system. Not merely through imagination or the simulated realms of theatres and planetaria, but with genuine spaceships. Still, we will go on these exploratory trips because we are interested and want to learn. Not because powerful aliens told us to go to the gas giants in the outer solar system and pointed out their huge bodies. Regrettably, Jupiter's atmosphere poses a lethal challenge for life, characterized by intense vertical winds whose velocities render hurricanes trivial by contrast. Heat would swiftly obliterate intricate organic molecules, making life's emergence implausible. While it is conceivable that bacteria could arrive at Jupiter via meteorites from other locations, the vertical winds render their survival improbable. Such bacteria would experience ascent and descent between frigid and excessively heated cloud levels. The only theory about how life could survive in Jupiter's atmosphere is that it could float, allowing it to stay at the right height even when strong winds are up and down. Nonetheless, such buoyancy would necessitate substantial gas-filled sacs, resulting in the organism being colossal. Since we cannot conceive of a method for bacteria to endure, it appears improbable that huge, buoyant organisms will evolve initially. If they originated elsewhere and landed on Jupiter, they could survive. But there is no known way for such massive organisms to travel through space. Consequently, the majority of scientists deem Jupiter uninhabitable. For fundamentally similar reasons, Saturn is unlikely to be conducive to habitation. Uranus and Neptune. Uranus and Neptune appear to be improbable candidates for supporting habitability. Their atmospheres are far cooler than those of Jupiter and Saturn, mostly due to their increased distance from the Sun. If clouds containing liquid water droplets exist, they must be situated deep within their atmospheres, and vertical winds akin to those of Jupiter and Saturn, albeit at a slower velocity, are likely detrimental to any potential life. Nonetheless, Uranus and Neptune possess a potential habitable zone that Jupiter and Saturn do not. Their outer cores are water, methane, and ammonia. Theoretical simulations indicate that these materials could exist in a liquid state, resulting in unusual oceans within the deep innards of Uranus and Neptune. Life is unlikely in these oceans because of the high pressures, a strange mixture of liquids, and lack of any obvious way to get energy from them. But it's still possible. If such life exists, our knowledge will be fleeting. No one has devised a feasible method to investigate planetary cores. Is it possible for life to exist on moons or other minor celestial bodies? The outer solar system comprises several minor celestial bodies, including the moons of the Jovian planets, asteroids, comets, and dwarf planets, such as Pluto and Eris. Can any of these worlds support life? The most promising prospects for habitability are some of the substantial moons of the Jovian planets. This may appear unexpected when considering their dimensions. Even the largest of these moons, Ganymede, orbits Jupiter and is marginally larger than Mercury, leading one to anticipate that all of them would be as geologically inactive as Mercury and the Moon. In contrast to the terrestrial planets, the moons of the Jovian planets originated with substantial ice, as they developed in regions of the solar system where temperatures were sufficiently low for ice to condense from the solar nebula. Due to ice melting at significantly lower temperatures than metal or rock, these moons can exhibit internally driven ice geology with considerably less internal heat than required for the rock geology of terrestrial planets. Moreover, many Jovian moons, particularly Jupiter's Io and Europa, possess a continuous interior heat source, distinct from those on terrestrial planets. We shall examine this phenomenon, referred to as tidal heating. The accessible heat can, theoretically, convert underlying ice into liquid water. In at least one instance, Europa, existing data clearly indicate a profound underground ocean of liquid water. Several medium to large moons in the outer solar system, show signs of geological activity that may have made it possible for a liquid medium to exist, or is still making it possible. The potential for habitability on certain huge moons is so promising that we will postpone their discussion to focus on them exclusively. The outlook is less favorable for the more abundant, yet considerably smaller moons, warranting their classification with other minor celestial entities within the solar system. Our biological exploration now leads us to the myriad tiny celestial bodies of the outer solar system. This group will also include Mars's two small moons, Phobos and Deimos, as they were formerly separate asteroids orbiting the Sun. It is hypothesized that Mars acquired them early in its history, when it possessed a substantial atmosphere that generated the friction required to decelerate passing asteroids sufficiently for them to become moons. Minor celestial bodies are improbable candidates for habitability at present. Most of them, especially the comets from the Kuiper Belt and Oort cloud, circle so far from the Sun that they are always frozen solid. This is because they are too small to hold any heat that could melt ice. Melting may only occur after infrequent encounters or within the interiors of comets, whose original orbits have been sufficiently altered to propel them into the inner solar system. Nevertheless, in such instances, any melting would persist for durations that appear insufficient for the emergence of life. The potential for life on small celestial worlds may have been more favorable in the past, although it still appears improbable. We have a lot of proof that both asteroids and comets contain complex organic compounds. Also, studies of meteorites show that a lot of them likely contained liquid water in the early days of the solar system. Liquid water may have endured for durations extending to tens of millions of years. Is it possible that life originated at that time? While we cannot dismiss the possibility, we have uncovered no evidence of past life in meteorites from the asteroid belt, and the majority of scientists deem it improbable that life could have originated on any of the myriad tiny bodies inside the solar system. We have concluded our succinct biological exploration of the solar system. Even though all worlds, no matter how big or small, have the basic chemical elements needed for life, the chances of life on them are much lower. When we look at the environmental conditions needed for life on Earth, the necessity for liquid water or an alternative liquid medium precludes the existence of life on the myriad minor celestial bodies inside our solar system. We have likewise excluded the possibility of life on Mercury and the Moon, and deemed life improbable on the Jovian planets. This results in minimal prospects for life in Venus's atmosphere, contrasted with somewhat greater possibilities for life on Mars and certain moons of the Jovian planets. These situations will be addressed in the subsequent chapters. Throughout our biological tour, we examined numerous aspects of the various realms within our solar system, which will be elaborated upon in greater detail in the subsequent 3 chapters. What methods have facilitated our extensive knowledge of these objects? Much of our knowledge is derived from telescopic studies conducted with ground-based telescopes in Earth's orbit, including the Hubble Space Telescope. In the case of our Moon, extensive knowledge has been acquired through the deployment of astronauts to investigate the landscape and retrieve samples for laboratory analysis. In other instances, we possess samples of distant celestial bodies that have arrived as meteorites, together with cometary dust retrieved by the Stardust mission. Nonetheless, most information driving the current transformation in our solar system comprehension originated from robotic missions. Thus far, we have dispatched robotic spacecraft to all 8 planets, numerous moons, asteroids, and comets. The New Horizons mission is presently traveling toward Pluto. This chapter's case study will succinctly examine the functionality of robotic spacecraft within the scientific process. What is the operational mechanism of a robotic spacecraft? The spacecraft dispatched for planetary exploration are robotic entities designed for extended space travel and equipped with specific instruments for scientific investigation. All spacecraft are equipped with power sources, including solar cells, propulsion systems, mechanisms for accurately orienting cameras and other equipment toward their targets, and computers that manage their primary components. Robotic spacecraft function predominantly based on pre-programmed directives. They utilize radios for communication, enabling them to receive further orders from Earth and transmit the data they gather. Most robotic spacecraft undertake unidirectional journeys from Earth, failing to return physically while transmitting data from space akin to global radio and television broadcasts. The robotic missions dispatched to investigate extraterrestrial realms are classified into four principal categories. Flyby. A spaceship executing a flyby traverses a celestial body only once before proceeding onward. Orbiter. An orbiter is a spacecraft that circumvents the celestial body it examines, facilitating prolonged study through several orbits. Lander or probe. These spacecraft are engineered to land on a planet's surface or investigate its atmosphere by traversing through it. Certain landers have transported rovers to investigate broader areas. A sample return mission necessitates a spacecraft to return to Earth with a specimen from the celestial body it investigated. The selection of a spacecraft type is contingent upon scientific objectives and financial considerations. A flyby is typically the most economical means of traveling to another planet, with certain flybys providing enhanced value by visiting numerous planets. Before departing from our solar system, Voyager 2 traversed Jupiter, Saturn, Uranus, and Neptune. Flybys are typically more economical than other missions due to their lower launch costs into space. Weight primarily influences launch expenses, with onboard fuel accounting for a substantial portion of a spacecraft's mass heading to another planet. Once a spacecraft is en route, the absence of friction or atmospheric drag in space allows it to sustain its orbital track throughout the solar system without expending any fuel. Fuel is necessary solely during the spacecraft's transition from one trajectory, orbit, to another. Furthermore, meticulous planning can utilize the planet's gravitational force to implement technological modifications. Upon examining Voyager 2's trajectory, one can observe that it underwent substantial alterations as it traversed Jupiter and Saturn. Consequently, it implemented these alterations without cost by utilizing gravity to alter its trajectory instead of consuming fuel. This method is called a gravitational assist. It accelerates the spacecraft considerably while imparting an imperceptible deceleration to the planet. The increase in velocity can be substantial. During its February 2007 flyby of Jupiter, the New Horizons spacecraft's speed increased by approximately 20%, reducing its travel time to Pluto by over 3 years. A flyby can yield significant scientific insights despite its brief duration for thorough examination. Flybys typically transport compact telescopes, cameras, and spectrographs. Due to their proximity to other celestial bodies, within tens of thousands of kilometers or less, this equipment may capture significantly higher resolution images and spectra than the greatest existing terrestrial telescopes. Moreover, flybys may provide data that would be challenging to acquire from Earth. For instance, Voyager 2 facilitated the discovery of Jupiter's rings and enhanced our understanding of Saturn's, Uranus's, and Neptune's rings through images illuminated by sunlight from behind them. Such perspectives are attainable only from outside the orbit of each planet. Flybys may transport sensors to assess local magnetic field strength or to collect interplanetary dust samples. The gravitational influences of planets and their satellites on the spacecraft yield data regarding the masses and densities of these objects. Similar to the illuminated perspectives of the rings, these data kinds are unattainable from Earth. Spacecraft traverse. An orbiter can examine another celestial body far longer than a flyby mission. Similar to spacecraft utilized for flybys, orbiters frequently possess cameras, spectrographs, and sensors designed to measure magnetic field intensity. Radar instruments equip certain orbiters. The radar transmits radio waves from the spaceship to reflect off the surface. The time the reflected signals return to the spacecraft indicates the distance they traversed, enabling accurate surface elevation measurements. Radar can penetrate dense cloud cover, as observed on Venus and Titan, and yield concealed topography insights. An orbiter is typically more costly than a flyby for an equivalent mass of scientific instruments, mainly due to the necessity of additional fuel to transition from an interplanetary trajectory to an orbital path around another celestial body. Meticulous preparation can mitigate the supplementary costs. Recent Mars orbiters have optimized fuel expenditures by carrying only sufficient fuel to achieve elliptical orbits around Mars. The spacecraft then established smaller, more circular orbits essential for scientific investigations by traversing the Martian atmosphere at the nadir of each elliptical orbit. Atmospheric drag decelerated the spacecraft during each orbit and over several months circularized its trajectory. The method of utilizing the atmosphere to decelerate the spacecraft and alter its trajectory is referred to as aerobraking. We have dispatched orbiters to every planet except Uranus and Neptune, as well as to the asteroid Eros. Spacecraft that deploy probes, wheels, cameras, and various sensors to investigate the Martian surface provide the most intimate examination of extraterrestrial environments. In 1995, the Galileo spacecraft, which orbited Jupiter for over 5 years, deployed a probe into Jupiter's atmosphere. This probe gathered data on temperature, pressure, composition, and radiation for approximately 1 hour during its descent, significantly enhancing our understanding of Jupiter's winds and atmospheric conditions, before succumbing to the planet's extreme interior pressures and temperatures. The Cassini spacecraft, presently in orbit around Saturn, also carried a probe named Huygens, which descended to the surface of Saturn's moon Titan, examining the atmosphere en route. The findings from Huygens will be discussed in detail when we focus on Titan. On planets with solid surfaces, a lander provides close-up surface observations, local meteorological assessments, and the capacity to conduct automated experiments. Certain landers are equipped with robotic rovers capable of traversing the terrain, exemplified by the Spirit and Opportunity rovers that landed on Mars in 2004 and continued to function over 6 years later as this book was published. Landers generally necessitate fuel to decelerate their descent to a planetary surface. However, innovative methods can mitigate costs. For instance, Spirit and Opportunity impacted Mars at crash landing velocity, but were safeguarded by airbags deployed during descent. Although probes and landers can perform experiments on surface rock or atmospheric samples, such experiments must be pre-designed, and the instrumentation must be accommodated within the spacecraft. These constraints lead scientists to yearn for missions to retrieve samples from extraterrestrial bodies and return them to Earth for comprehensive analysis. We possess a plethora of lunar rock samples gathered by Apollo astronauts and robotic spacecraft dispatched by the former Soviet Union. Nevertheless, we have not yet collected and returned samples from other moons or planets. In recent decades, numerous robotic spacecraft have investigated diverse celestial bodies within our solar system. Although not all missions were specifically aimed at astrobiology, every discovery enhances our comprehension of the potential for life in the universe. Mars. The concept of a civilization on Mars was previously regarded so seriously that the term Martians almost became interchangeable with extraterrestrial life. Spacecraft dispatched to Mars in the 1960s dismantled the fictional portrayal of a planet populated by cities and advanced life forms. Yet the potential existence of past or current microbial life on Mars remains a focal point of rigorous scientific inquiry and discourse. Significant evidence indicates that water previously flowed on Mars, and it appears probable that Mars originally possessed surface or subsurface conditions akin to those that supported life on early Earth. If life originated on Mars or was delivered via meteorites from early Earth, we may discover its fossilized remnants. Life persists on Mars, potentially in subterranean environments where volcanic heat maintains liquid water. I recall being captivated by the initial lander photograph depicting the Martian horizon. I concluded that this was not an extraterrestrial realm. I was familiar with locations similar to that in Colorado, Arizona, and Nevada. The terrain had rocks, sand dunes, and a remote elevation, exhibiting a natural and unself-conscious quality akin to any seen on Earth. Mars constituted a location. I would have been astonished to witness a weathered prospector emerge from behind a dune, guiding his mule, but the notion appeared fitting. Carl Sagan, 1934 to 1996. We have not yet arrived at the stage to conduct a conclusive search for life on Mars, yet we are swiftly acquiring knowledge about Mars and its history. This chapter will examine our current knowledge and its implications for the potential existence of life on Mars. Imaginations of Martian civilization. Mars has consistently captivated human imagination, radiating vividly and distinctly red in the nocturnal sky. A significant portion of contemporary knowledge regarding Mars is derived from observations conducted by robotic spacecraft. Interest in extraterrestrial life on Mars originated much earlier and remained a prominent element of popular culture for decades. In what manner did Mars permeate popular culture? The narrative commences with the distinguished English astronomer William Herschel, 1738 to 1822. Although primarily recognized for the discovery of the planet Uranus, Herschel made many additional astronomical discoveries, often with the assistance of his sister and colleague astronomer Caroline Herschel, 1750 to 1848. The Herschels frequently examined Mars with their telescopes, documenting its polar ice caps and determining that the duration of its day, 24 hours, 37 minutes, closely resembles that of an Earth day. In a presentation delivered to Britain's Royal Society in 1784, William Herschel asserted that Mars harbored an atmosphere and that its inhabitants probably enjoy a situation in many respects similar to our own. By referencing inhabitants, the prospect of extraterrestrial life on the red planet was introduced by a distinguished scientist in an academic context, leading to the assumption of Martian existence. Herschel's methodology for populating the cosmos lacked discernment. He believed all entities inside the solar system inhabited, including the Moon and the Sun. Mars ascended to prominence in astronomical studies during the subsequent century. In 1877, Italian astronomer Giovanni Schiaparelli asserted the observation of a network of 79 linear features termed canali, which translates to channels in Italian. However, this was frequently misinterpreted as canals. Following the excitement generated by the 1869 inauguration of the Suez Canal, Schiaparelli's discovery sparked visions of artificial waterways constructed by a Martian civilization. Schiaparelli remained doubtful of such assertions, and whether he believed the canals contained water is uncertain. Nonetheless, his findings captivated the imagination of a young Harvard alumnus, Percival Lowell, 1855 to 1916. Lowell, possessing a degree in mathematics, hailed from an affluent and esteemed New England lineage. His brother Abbott achieved prominence as the president of Harvard, while his sister Amy attained recognition as a poet. After several years as a businessman and traveler in the Far East, Percival Lowell transitioned to astronomy. Driven by his conviction in the existence of Martian canals and supported by his affluence, Lowell commissioned the construction of an observatory in Flagstaff, Arizona. He selected Flagstaff due to its arid environment and elevated altitude, which he believed would mitigate atmospheric distortion, facilitating the mapping of Martian canals. The Lowell Observatory commenced operations in 1894 and continues to function today. In the subsequent 2 decades, Lowell delineated approximately 200 canals he asserted to observe on Mars, releasing his inaugural book on the subject in 1895. Assuming that Mars's polar caps resembled Earth's and consisted of water ice, he envisioned the canals as conduits for transporting water from the poles to arid towns closer to the equator. Envisioning the Martians as an ancient culture on a planet teetering on the brink of extinction was a rational progression. The worldwide system of canals led Lowell to believe that the Martians constituted members of a unified global nation. Such concepts furnished the scientific foundation for H.G. Wells's The War of the Worlds, released in 1898. The widespread public belief in Martians culminated in a notable panic decades later, triggered by a radio broadcast of the War of the Worlds, when numerous individuals perceived an invasion imminent. Lowell was a proficient proponent of the canals, yet they are not genuinely extant. Even in his own day, contemporaneous scientists disputed most of Lowell's assertions. A significant issue was that most astronomers did not observe any canals when they utilized telescopes, even those larger than Lowell's, and the canals did not appear in photographs taken through telescopes. Moreover, several scientists challenged Lowell's fundamental assumptions and conclusions. In 1907, Alfred Russel Wallace, co-discoverer of evolution by natural selection alongside Darwin, employed physical reasoning to propose that Mars is likely too frigid for liquid water to exist. He highlighted a significant flaw in Lowell's interpretation of the canals. Lowell's canals adhered to straight-line trajectories over extensive distances, but actual canals would be constructed to conform to the contours of natural topography, for instance, circumventing mountains. Wallace encapsulated this argument. A network of canals, as Mr. Lowell depicts, would be the endeavor of lunatics. What was Lowell observing? In a few instances, his canals align with actual characteristics on Mars. The canal he frequently observed, called Agathodemon, corresponds with the site of the extensive canyon system currently identified as Valles Marineris. Several canals align with Martian topography. Nevertheless, most were figments of imagination. A telescopic photograph of Mars with one of Lowell's cartographic representations of the identical areas. The alignment of the dark and bright sections in the photograph and the illustration is evident, although perceiving any canals necessitates a strong imagination. Lowell's narrative exemplifies the challenges and successes of contemporary science. Individual scientists may still include personal prejudices in their scientific endeavors, despite their sincerity and commitment. In Lowell's instance, he was so resolute in his belief in the existence of canals and Martians that he disregarded any alternative evidence. However, the conclusion of the narrative illustrates the reasons behind the success of contemporary science. Notwithstanding Lowell's prominence, other scientists did not acknowledge his faith assertions other scientists did not acknowledge. They aimed to validate his observations and examine his foundational assumptions. It was determined that Lowell's assertions were deficient in every respect. Consequently, Lowell became an increasingly solitary voice while promoting an erroneous perspective. A contemporary representation of Mars. The public discourse over Martian canals and cities remained unresolved until NASA dispatched spacecraft to Mars. In 1965, NASA's Mariner 4 spacecraft approached within 6,000 miles of the Martian surface, relaying several dozen television-quality photographs of the terrain underneath. The surface of Mars appeared strewn with craters rather than canals, and the spacecraft's observations of atmospheric pressure and temperature suggested a cold, arid planet seemed unable to sustain life. Nonetheless, the possibility of life on Mars persisted. No indication of sentient life was found. Nonetheless, the tenuous atmosphere and polar caps suggest the potential existence of bacteria, rudimentary flora, or fauna. On July 20th, 1976, 7 years after Neil Armstrong's historic lunar walk, and nearly a century following Schiaparelli's depiction of canali, a NASA space mission traversed the tenuous atmosphere of Mars. The Viking 1 lander landed in Chrysaor Planitia, an extensive rocky plain around 1,300 kilometers north of the Martian equator. 2 months later, Viking 2 alighted on the opposite hemisphere of the planet. Simultaneously, 2 Viking orbiters examined the planet from an aerial perspective. Upon activation, the Viking lander's cameras revealed a desolate terrain characterized by crimson dust and dispersed pebbles in the chilly mountain atmosphere. No critters were observed gazing at the cameras, nor were any plants clustered in the feeble sunshine. The visuals persisted for months. However, the perspective remained largely unchanged. No growth occurred, save for sporadic frost spots, and no movement transpired aside from wind-driven dust. Although neither lander could move from its landing site, each had a robotic arm to collect soil samples for onboard studies to detect bacteria. The Viking orbiters and landers yielded substantial scientific data regarding Mars. However, they also left other problems unresolved, and the scientific community was eager for subsequent missions. Regrettably, financial and political factors, coupled with the unsuccessful Russian missions to Mars, Phobos 1 and 2, and the American mission, Mars Observer, collectively halted spacecraft investigation of Mars for approximately 2 decades. The prolonged mission hiatus concluded on July 4, 1997, with the landing of Pathfinder and its little rover, Sojourner. Named after Sojourner Truth, an African-American icon of the Civil War period, the rover could traverse only a few tens of meters, sufficient to analyze the chemical compositions of local rocks. Since Pathfinder, over 6 additional robotic spacecraft have successfully reached Mars. By integrating data from current missions with historical data, we are commencing the construction of an accurate depiction of Mars's past and present habitability. What is the current state of Mars? The current landscape of Mars resembles certain deserts or volcanic plains on Earth. Nevertheless, its tenuous atmosphere renders it distinct from any location on Earth. Table 8.1 encapsulates fundamental data regarding Mars. The surface temperature typically remains much below freezing, and the atmospheric pressure is under 1% of that on Earth, resulting in an atmosphere so tenuous that no human could endure exposure for more than a few minutes without a pressurized spacesuit. The atmosphere comprises merely trace quantities of oxygen, rendering it unbreathable. The absence of oxygen on Mars results in the non-existence of an ozone layer, allowing significant amounts of the sun's harmful UV radiation to reach the surface unimpeded. Nonetheless, Martian circumstances are significantly less severe than those on the Moon, primarily because of the atmospheric moderating effects. It is plausible to see future people residing and operating within airtight research stations, while occasionally utilizing spacesuits for outside activities. The surface gravity on Mars is approximately 40% of that on Earth, resulting in a corresponding weight reduction to 40% of Earth's weight for all objects and individuals. Astronauts could traverse effortlessly while donning spacesuits equipped with substantial backpacks. Adapting to diurnal and nocturnal rhythms would be straightforward, given a Martian day exceeds an Earth day by around 40 minutes. The absence of surface. Liquid water. The diminished atmospheric pressure elucidates a crucial aspect pertinent to the quest for extraterrestrial life on Mars. Liquid water is currently absent from the Martian surface. We ascertain this not just via extensive study of the surface, but also due to the surface conditions that preclude the existence of liquid water in the form of lakes, rivers, or puddles. In numerous locations and at various times, Mars experiences temperatures that exceed freezing, particularly during midday near the equator. At the equator, the atmospheric pressure is sufficiently low that liquid water rapidly evaporates. In other words, when both factors are considered, liquid water is currently unstable on Mars. Nonetheless, as will be elaborated momentarily, Mars probably possessed liquid water in its history and still contains substantial water ice, some water vapor, and potentially even subterranean reservoirs of liquid water. Martian seasons and winds. Earth has seasons due to the inclination of its axial tilt. The Earth's axis consistently points toward Polaris throughout the year, making the northern and southern hemispheres oriented toward the Sun on different ends of its orbit. Summer occurs when your hemisphere is tilted toward the Sun, while winter occurs when it is tilted away. The axial tilt of Mars closely resembles that of Earth, measuring 25 degrees compared to Earth's 23.5 degrees, resulting in analogous seasonal variations. Nonetheless, Martian seasons diverge from Earth seasons in two significant aspects. Due to the Martian year being almost twice the duration of an Earth year, each season on Mars persists for nearly double the length. Secondly, although Earth's nearly circular orbit indicates that axial tilt is the sole significant factor influencing our seasons, Mars's seasons are additionally influenced by the eccentricity of its orbit. Mars is considerably nearer to the Sun during its southern hemisphere summer and more distant during its southern hemisphere winter, 8.7. Due to the accelerated orbital velocity of planets near the Sun, as articulated in Kepler's second law, Mars's southern hemisphere experiences more pronounced seasonal variations, characterized by shorter, warmer summers and longer, colder winters compared to its northern hemisphere. The seasonal transitions result in several significant characteristics of Martian meteorology. At the winter pole, temperatures plummet to approximately -130 degrees Celsius, causing carbon dioxide to condense as dry ice at the polar cap. This phenomenon accounts for the significantly larger size of the polar caps in winter compared to summer, figure 8.8. Simultaneously, frozen carbon dioxide near the summer pole undergoes sublimation, transitioning straight from solid to gaseous state into carbon dioxide gas. And during the height of summer, just a remnant layer of water ice persists. Consequently, air pressure rises near the summer pole and diminishes at the winter pole. Approximately 1/3 of the total carbon dioxide in the Martian atmosphere migrates periodically between the northern and southern polar caps. The intense winds linked to the cycling of carbon dioxide can trigger significant dust storms, especially as the more severe summer season approaches in the southern hemisphere. Occasionally, the Martian surface is nearly entirely concealed by flying dust. As the dust accumulates, it can alter the surface look across extensive areas, for instance by obscuring dark parts with lighter dust. Such alterations misled prior astronomers into believing they observed seasonal variations in vegetation. The Martian winds can generate dust devils spinning gusts similar to those observed over desert sands or arid soil on Earth. Dust devils resemble little tornadoes, yet they ascend from the ground instead of descending from the sky. The air within dust devils is thermally elevated from beneath by the solar-heated ground, and dust devils rotate due to the interaction of the ascending air with prevailing winds. Dust devils on Mars are particularly prevalent during the summer in either hemisphere and can be significantly larger than those on Earth. The Mars rovers have captured images of dust devils, some seemingly traversing directly over the rovers without inflicting damage. In one instance, a dust devil seemingly cleansed the dust from the solar panels of the rover Spirit, reinstating power that had been diminished due to dirt accumulation. Hue of the Martian atmosphere. Winds and dust storms render Mars's atmosphere consistently gritty, elucidating the hues of the Martian sky. In the absence of suspended dust, the Martian atmosphere is so tenuous that the sky would seem predominantly black, even during daylight hours. Rather, light diffused by the airborne particulates typically imparts a yellow-brown hue to the sky. Variations in hues can arise due to fluctuations in the quantity of suspended dust throughout morning and evening hours. The photograph of the Martian sunset that starts this chapter depicts the picture as it would seem to the human eye, but with slightly enhanced colors. What are the principal geological characteristics of Mars? Mars's surface may seem dismal and arid, but it was not always in this state. Numerous surface features have been sculpted by liquid water, prompting scientists to deduce that Mars likely possessed a more pleasant environment in the past. Before examining the evidence for surface water and theories regarding Mars's climatic history, it is beneficial to orient ourselves by analyzing the planet's prominent geographic features. The complete surface of Mars, with the poles positioned at the top and bottom and the equator traversing horizontally through the center, is illustrated in a way akin to an atlas representation of the entire globe of Earth. Mars's surface area is 1/4 that of Earth due to its diameter being half that of Earth. Water, encompassing almost 3/4 of Earth's surface, means Mars possesses a total land area comparable to that of Earth. Following the polar caps, the most notable characteristic is the considerable variation in the landscape across various regions of Mars. Most of the southern hemisphere features elevated terrain and is marked by numerous substantial impact craters, notably the Hellas Basin. Conversely, the northern plains have a scarcity of impact craters and are generally situated below the typical Martian surface elevation. Crater crowding indicates surface age. Mars was previously uniformly populated with craters, suggesting that most of the ancient craters in the northern plains have been obliterated by more recent geological processes. Consequently, the extensively cratered southern highlands represent an older surface than the northern plains. Volcanism was the primary factor responsible for obliterating ancient craters on Mars, although tectonics and erosion contributed as well. The northern plains exhibit characteristics typical of lava flows, indicating that outbursts of highly fluid lava obscured the pre-existing impact craters. Notably, faint ghost craters are observable in certain locations, indicating that the lava flows lacked sufficient thickness to entirely obliterate the underlying structures, affirming that the planet was formerly heavily cratered. Numerous enigmas persist nonetheless. For instance, the reasons behind the differential impact of volcanism on the northern plains compared to the southern highlands and the significant elevation disparity between the two locations remain unknown. Additional evidence of volcanic activity on Mars is provided by its colossal volcanoes. Volcanoes may likely be identified by their dome shapes and central calderas, the craters at their centers. Many volcanoes are situated on or adjacent to the continent-sized Tharsis bulge. Tharsis, commonly referred to as such, spans around 4,000 kilometers in diameter, with much of its expanse elevated several kilometers above the mean Martian surface elevation. A long-lived plume of ascending mantle material formed by distorting the surface upward and supplying molten rock for the eruptions that constructed the colossal volcanoes. The Tharsis volcanoes surpass any located on Earth. Olympus Mons, the greatest of them, is the highest recognized mountain in the solar system. Its summit ascends around 26 kilometers above the mean Martian surface level, roughly 3 times Mount Everest's elevation above sea level on Earth. The base spans around 600 kilometers, sufficient to include an area equivalent to that of Arizona, and is bordered by a cliff that reaches heights of up to 6 kilometers in certain locations. 2 variables elucidate why Martian volcanoes surpass those on Earth in size. The decreased gravity on Mars enables the erection of lofty edifices. The absence of plate tectonics on Mars results in immobile mantle plumes relative to the surface, leading to the formation of massive singular mountains. Conversely, the progressive movement of Earth's crust owing to plate tectonics causes a single mantle plume to create a chain of volcanic islands. Located east of Tharsis and somewhat south of the equator is the extensive profound system of valleys known as Valles Marineris. Valles Marineris, named after the Mariner 9 spacecraft that first captured its images, spans a length equivalent to the width of the United States and is nearly 4 times deeper than the Grand Canyon. The precise formation of valles marineris is uncertain. Nonetheless, its geographical position indicates a connection to the Tharsis Bulge. It likely developed due to tectonic forces associated with the uplift of material that formed Tharsis, fracturing the surface and resulting in the steep cliff walls of the valleys. Several characteristics of the valley network have been sculpted by flowing water, and orbital spectra indicate the existence of minerals produced in aqueous conditions. Certain canyon walls display stratification, likely resulting from sedimentary layers or successive lava flows. The canyon is so profound that, if uplift was responsible for its formation, portions of its walls must have been several kilometers below the surface, perhaps subjected to liquid water. Consequently, valles marineris could be one of the most promising locations to search for fossil evidence of former Martian life. We can discern the mechanisms that influenced surface formation and their temporal occurrence by analyzing the geological features of Martian surfaces of varying ages. For instance, we can examine characteristics that signify volcanic eruptions, such as lava flows or volcanoes, and infer the history of volcanism. Research indicates that the incidence of volcanic eruptions on Mars has progressively diminished since approximately 3.5 billion years ago, consistent with expectations for a planet of size that has likely dissipated much of its core heat by this time. Nonetheless, Mars may not be entirely geologically inactive, which carries significant implications for the potential existence of Martian life. While Martian volcanoes exhibit a sufficient number of impact craters on their slopes, indicating prolonged inactivity for at least tens of millions of years, the examination of Martian meteorites suggests another viewpoint. Radiometric dating of these meteorites indicates that some consist of volcanic rock formed from molten lava as recently as 180 million years ago, relatively recent in the 41 billion year history of the solar system. This indicates that Mars continues to possess residual interior heat. It is uncertain whether it is sufficient to trigger future volcanic eruptions, but it is highly likely to melt some subterranean ice into liquid water. What evidence indicates that water previously flowed on Mars? We now focus on the evidence that instills confidence in scientists regarding the existence of significant quantities of flowing water on Mars in the past. This data positions Mars as a leading contender in the quest for past or current extraterrestrial life. The initial evidence of historical water was derived from images captured by Mariner 9 and the Viking orbiters, which displayed formations resembling arid riverbeds on Earth as observed from an aerial perspective. Recent orbiters have captured images of these channels with significantly enhanced resolution, figure 8.16b. Thorough analysis suggests that running water likely formed the channels. Although the origin of the water, whether from rainfall runoff, erosion by water-laden debris flows, or a subterranean source, remains uncertain. Analysis of the crater counts within and adjacent to the channels indicates they are at least 2 to 3 billion years old, suggesting that water has not traversed them since that period. Nonetheless, they convey a significant narrative regarding Mars's history. Their intricate and winding characteristics imply they were formed over time, suggesting that liquid water was stable at or beneath the surface. The current low temperature and atmospheric pressure render liquid water unstable, leading us to assume that Mars must have possessed a significantly warmer and denser atmosphere at certain periods in its ancient past. A meticulous analysis of impact craters further substantiates that Mars has surface water in the distant past. The ancient, extensively cratered southern highlands encompass a vast area. Observe the unclear edges of numerous large craters and the comparative scarcity of minor craters. Certain experts hypothesize that precipitation may have worn these craters, while wind or glaciers could have also contributed to the erosion. Compelling evidence supports the existence of lakes within the depths of several craters. A three-dimensional view of the surface indicates that water originally traversed between two primordial crater lakes. Further compelling evidence is derived from photos and spectra that reveal the mineral makeup of the Martian surface. Numerous locations on Mars have identified three primary categories of hydrated minerals: clay minerals, hydrated sulfates, and hydrated silica, generally referred to as opal. These minerals include water or hydroxide, O, indicating their formation in liquid water. The green color coding indicates the presence of clay minerals, likely deposited by sediments traversing channels and valley networks. The opaline minerals hold great significance for two reasons. Initially, it is believed they originate in hot springs or hydrothermal settings. Note that such habitats may have played a crucial role in the emergence of life on Earth. Secondly, certain places where they are located seem to have developed up to 1 billion years after the dense old clay deposits were formed. If this timeline is validated, it would indicate that Mars had moisture for a protracted duration throughout its primordial history, allowing greater opportunity for life to emerge and develop. Figure 8.18 illustrates an area where the Mars Reconnaissance Orbiter identified opal near Valles Marineris. The twin robotic rovers Spirit and Opportunity have validated and expanded the mineral evidence of historical water presence. Spirit alighted in Gusev Crater, the presumed ancient lake. The Opportunity rover arrived at the Meridiani Plains, where orbital spacecraft identified hematite, an iron-rich mineral often formed in aqueous environments but capable of volcanic formation. Both rovers were outfitted with cameras, equipment for determining rock composition, and a grinder to reveal fresh rock for examination. A primary objective of Opportunity was to ascertain whether the hematite at its landing site originated in water or through another process. The evidence unequivocally indicates the water. The rocks at the Opportunity landing site exhibit a stratified structure and peculiar indentations suggestive of aqueous development. At the same time, their composition indicates the presence of hematite and other minerals, including the sulfur-rich mineral jarosite, which often forms in aquatic environments. Notably, the rock comprises minuscule hematite spheres, colloquially termed blueberries, although neither blue nor comparable in size to commercial berries. They closely resemble both in appearance and composition the hematite spheres on Earth. The specimens on Earth evidently originated in aquatic environments, and a comprehensive examination of the structure and content of the Martian blueberries suggests they arose comparably. Subsequent research by Opportunity suggests that the water was likely shallow and perhaps acidic or saline, indicating that the rover landed in an area formerly a pond or shallow lake. Spirit has also revealed significant mineral evidence, particularly identifying opaline minerals and hydrated sulfates in the Gusev crater called Home Plate. These minerals and additional geological indicators strongly support the hypothesis that the Home Plate was formerly a volcanically heated thermal hot spring site. Notably, the rover's footprints appear to have disrupted certain mineral evidence. The evidence for historical liquid water on Mars is compelling. Was the water shallow and confined or extensive and profound? Did it exist sporadically in liquid form? Or were there lakes or even seas that persisted for millions of years? A significant controversy persists regarding these inquiries, and the Martian surface presents contradictory evidence. Numerous locations on Mars exhibit signs of having experienced devastating floods. An area near the summit of a lengthy valley, designated as Ares Vallis, is characterized by outflow canals that resemble those formed by floodwaters on Earth. Investigating the channels upstream to their origin uncovers a terrain devoid of remnants of a former lake or reservoir, indicating that the floodwaters originated from subterranean sources. The Pathfinder mission, which landed downstream in 1997, provided additional evidence for the flood idea by uncovering a wide floodplain characterized by rocks dispersed and arranged similarly to those observed post-flood on Earth. The time and origin of historical floods remain ambiguous. Nevertheless, other photos indicate a correlation between volcanic heating and some floods. The volcano possesses multiple downhill channels that radiate outside from its primary caldera. A far broader canal is observed in the lower right, perhaps formed by floodwaters released during one or more eruptions. These characteristics indicate the former presence of subterranean reservoirs of liquid water adjacent to volcanoes. A possible environment for life. If Martian volcanoes maintain sufficient heat, such water reservoirs may remain there. To assess the volume of water that may have once flowed on Mars, scientists can examine the water ice that persists today. Water ice is in and around the polar caps, and orbital investigations indicate a substantial quantity in the Martian subsoil across much of the planet. The complete scope of the water ice is just starting to be elucidated. Researchers were astonished to see ice directly beneath the Phoenix lander upon its arrival in the Martian Arctic in 2008. Phoenix was not a rover, and hence could not investigate its environment. However, it appears probable that ice is prevalent in the Arctic region, either intermixed with the surface soil or concealed beneath a layer of dust. If melted, the ice now identified on Mars would yield sufficient water to form an ocean 11 meters deep across the entire planet. Did an ocean ever exist? Compelling evidence suggests that numerous extensive flood channels have emptied into the northern plains, and a color-coded elevation map implies that these plains previously contained an ocean. Endorsement for the contentious ocean hypothesis has varied over the last 10 years. The hypothesis regained prominence when this book was published, due to a newfound acknowledgement of the quantity and density of river networks on Mars. More widespread networks enhance the probability that the rivers originated from global precipitation, raising the likelihood that water may have formerly occupied an ocean basin. A pertinent dispute pertains to the existence of water on Mars. As will be discussed shortly, there is uncertainty regarding whether Mars ever possessed an atmosphere sufficiently warm and dense to maintain stable, liquid water on its surface. If it had not, water flows could only have been sporadic, and lakes or seas could not have endured the millions of years scientists hypothesize would be requisite for life to emerge. However, even if the environment once permitted water to remain for prolonged durations, that epoch likely concluded at least 2 to 3 billion years ago. Although most evidence for historical water originates from older surface regions, several flood zones are more recent. In that scenario, the floods were likely ephemeral. Water may have surged from subterranean sources, perhaps due to a meteorite strike, enduring just briefly to sculpt channels and other surface formations before freezing or evaporating. Recent hydrological flows? No evidence of extensive water flows on Mars has been uncovered for the past billion years. Nonetheless, the extensive presence of water ice and the potential retention of volcanic heat on Mars suggest that intermittent small-scale water flows may still transpire. Recent evidence of water flow is most compelling, as indicated by photographs of gullies on crater and channel walls. These gullies resemble those that develop following precipitation on nearly any degraded slope on Earth. Orbital photographs of the same Martian regions taken just a few years apart frequently reveal the emergence of fresh gullies, indicating that they are actively evolving. One explanation posits that the gullies develop as snow accumulates on the crater walls during winter and melts from the snowpack base in spring. If this concept is accurate, the water at the base may melt instead of sublimating immediately into water vapor, as ice often does on Mars, due to the angle of sunlight and the pressure from the above snow. Alternatively, landslides, which transpire in other regions of Mars seasonally, may create the gullies. Although water occasionally flows, Mars was evidently significantly warmer and wetter in the past compared to its current state. Ironically, Percival Lowell's hypothesis regarding Mars's desiccation has proven accurate, but in a manner markedly divergent from his original conception. Although our understanding of water on Mars's historical timeline remains incomplete, the data presented indicates that liquid water was stable, or fairly stable several times, approximately 2 to 3 billion years ago. The air pressure and temperature must have been much elevated for such to occur compared to present levels. Historically, Mars presented a significantly more benign climate than it currently does, perhaps conducive to the emergence and establishment of life. What factors contributed to Mars becoming warmer and wetter in its historical period? While it is straightforward to deduce that Mars was likely warmer and wetter in the past, elucidating the reasons for this phenomenon is more complex. The fundamental explanation likely resides in the greenhouse effect, which can significantly elevate a planet's surface temperature. A modest greenhouse effect prevents Earth from freezing, whereas an excessive greenhouse effect causes extreme temperatures on Venus. Mars has an exceedingly tenuous atmosphere, resulting in a feeble greenhouse effect, despite 95% of its atmospheric composition comprising the greenhouse gas carbon dioxide. Nonetheless, Mars likely experienced a significantly more potent greenhouse effect in its historical epoch. Calculations indicate that Martian volcanoes should have released sufficient carbon dioxide to render the atmosphere around 400 times denser than it is currently, along with enough water to create oceans several tens to hundreds of meters deep. If Mars possessed this quantity of carbon dioxide currently, its surface pressure would be approximately 3 times that of Earth, and its temperature would exceed freezing, thus creating a climate conducive to the flow of liquid water. Nevertheless, due to the belief that the Sun was less luminous in the ancient past, additional greenhouse warming would have been necessary to permit the existence of liquid water during Mars's formative years. Existing models cannot explain further warming attributed solely to carbon dioxide gas. Numerous experts assert that carbon dioxide, ice clouds, and methane gas contribute to increased warming via their greenhouse effect. Alternatively, it is possible that Mars never experienced a prolonged warm period, but rather only sporadic wet intervals, potentially induced by the thermal effects of significant impacts. However, the data we have uncovered about substantial water flows indicates that Mars's atmosphere was significantly thicker and warmer in the distant past compared to its current state. What caused the transformation of Mars? Considering that Mars must have previously possessed a significantly denser atmosphere with a more pronounced greenhouse effect, the current markedly disparate conditions can only be elucidated if Mars somehow expended a substantial amount of carbon dioxide gas. This loss would have diminished the greenhouse effect, potentially leading to planetary freezing. Where has all this gas disappeared to? Some carbon dioxide has condensed to form the polar caps. Some may be chemically bonded to surface rock, and a fraction continues to constitute the Martian atmosphere. The exact mechanism by which Mars lost its carbon dioxide gas remains ambiguous. Nonetheless, significant impacts likely expelled some of it. Recent findings indicate that a more significant loss mechanism was associated with a modification. The magnetic field would have diminished as the small planet cooled and core convection halted, rendering the atmosphere susceptible to solar wind particles. Solar wind particles may have eroded gas from the Martian atmosphere into space. Mars has irrevocably depleted a significant portion of its water supply. The solar wind may have eroded some water vapor, analogous to its effect on carbon dioxide. Nonetheless, Mars also expunged water through another mechanism. Due to the absence of an ultraviolet-absorbing stratosphere on Mars, atmospheric water molecules would have been readily dissociated by ultraviolet radiation from the Sun. The little hydrogen atoms detached from the water molecules would have rapidly dissipated into space via thermal escape. Low-mass gas atoms can attain escape velocity and enter space. Section 4.4. The water molecules could not be restored to their entirety without these hydrogen atoms. Initially, oxygen from water molecules would have persisted in the atmosphere. However, this oxygen was depleted with time. The solar wind likely removed some of the atmosphere's oxygen, while the remainder was presumably extracted by chemical reactions with surface minerals. The oxygen oxidized the Martian rocks, imparting the red planet its characteristic hue. Our concept posits that Mars underwent significant alterations due to its diminutive size. It was sufficiently large for volcanism and outgassing to emit substantial water and atmospheric gases early in its lifetime, yet too tiny to retain the necessary internal heat. The Moon's surface area to volume ratio is approximately 4 times larger than Earth's, indicating that the Moon would cool 4 times more rapidly, assuming all other factors remain constant. Indeed, Earth has kept heat for an extended duration due to its greater size, which provided an initial heat surplus and its elevated concentration of radioactive elements. As its interior cooled, its volcanoes became dormant and emitted significantly less gas into the atmosphere, while its comparatively feeble gravity and the depletion of its magnetic field permitted the existing gas to be expelled into space. Mars may possess a temperate temperature if it had been as massive as Earth, allowing for outgassing and a worldwide magnetic field. The distance of Mars from the Sun has significantly influenced its destiny. Despite its diminutive size, Mars may possess flowing water if it were situated considerably closer to the Sun, where the additional warmth might thaw the water trapped below and at the polar ice caps. With the gas that formerly warmed the planet now absent, there is no hope that Mars will regain a warm, humid environment. Recent research indicates that Mars continues to experience substantial temperature change during geologically brief intervals of hundreds of thousands of years. This temperature shift results from alterations in axis tilt and may have considerable ramifications for Mars's eventual habitability. Earth undergoes prolonged climate cycles, such as ice ages, due to minor alterations in its rotation and orbit, including slight variations in axial tilt. The tilt of Earth's axis remains relatively constant, fluctuating between 22 degrees and 25 degrees, due to the stabilizing gravitational influence of our big moon. Mars lacks a substantial moon, and its 2 diminutive moons, Phobos and Deimos, are insufficiently sized to stabilize its rotational axis. Furthermore, due to Mars's proximity to Jupiter compared to Earth, Jupiter's gravity exerts a more significant perturbation on Mars during its solar orbit. Estimates indicate that the absence of a stabilizing moon and the influence of Jupiter will result in Mars undergoing significant fluctuations in its axial tilt over periods ranging from 100,000 to 1 million years. Models indicate that the axial tilt of Mars fluctuates between 0 degrees and 80 degrees, rendering the current tilt of 25 degrees considerably less than the average. The alterations in tilt would significantly impact the climate. When Mars's axial tilt is minimal, the poles may remain in continuous deep cold for millennia. The accumulation of frozen carbon dioxide at the poles results in a diminished atmospheric density, reducing pressure and attenuating the greenhouse effect. When the axis is significantly inclined, the summer pole attains sufficient warmth to facilitate the sublimation of considerable quantities of water, ice, and carbon dioxide into the atmosphere. Consequently, the pressure escalates, increasing the temperature on Mars as the greenhouse effect intensifies. The polar regions of Mars exhibit stratification that likely indicates climatic variations resulting from alterations in axial tilt. Even at extreme inclinations, the air pressure remains insufficient to permit the accumulation of liquid water in surface lakes or ponds. Models indicate that liquid water may exist close below the surface or at rock ice interfaces whenever the tilt exceeds approximately 40 degrees. Given that a 40-degree tilt value is likely the norm over time, Mars may possess regions of liquid water during most epochs. Is Mars suitable for habitation? Mars possesses the essential components for life. Energy is accessible via sunlight on the surface. and chemical energy, subterranean. Mars's habitability ultimately depends on the presence of liquid water. Geological evidence clearly indicates that Mars formerly possessed substantial liquid water on its surface, implying that the planet was habitable approximately 2 to 3 billion years ago. The sole inquiry pertains to whether it was conducive to habitability over an extended duration, thereby rendering an indigenous origin of life possible, or merely during brief, sporadic intervals. Mars may have been habitable only on rare occasions if water had been present only sporadically, such as in the following impacts. However, if water had existed for millions or tens of millions of years, then early Mars may have resembled early Earth. Consequently, Mars might have been conducive to life while life emerged on Earth. The absence of liquid water renders the surface of Mars uninhabitable at now. Nonetheless, evidence indicates that reservoirs of liquid water may persist subterraneously, maintained at elevated temperatures by geothermal activity. Consequently, Mars may possess subterranean regions conducive to habitability. Furthermore, the climatic alterations associated with the shifting magnetic axis tilt suggest that spanning geological epochs, Mars may retain minimal quantities of surface water at rock-ice interfaces, approximately 50% of the time. On Earth, bacteria inhabit tiny films of liquid water at boundaries, suggesting the fascinating prospect that Mars may possess surface habitable zones during various epochs. Unless we significantly misread the evidence, the conclusion appears unequivocal. Mars's surface was conducive to habitation during some epochs of its early history, and it may still occasionally be suitable for habitation when the axial tilt is more pronounced. The subsoil likely harbors livable zones even at present. Considering Mars's perceived potential for habitability, we must concentrate on the quest for tangible life. Although scientists have some confidence regarding Mars's past and present habitability, we remain uncertain whether life has existed. The sole method to ascertain the existence of former life is to investigate fossil evidence within Martian rocks, whereas the exclusive means to determine the presence of current life is to discover it directly. Future explorations for life on Mars will be significantly more comprehensive than current endeavors. Is there any proof of extraterrestrial life on Mars? The discovery of life on Mars would fundamentally transform our perception of life in the universe. Hence, it is unsurprising that numerous scientists are striving to be the first to uncover proof of this significant finding. Should life on Mars exist? As we will discuss, some scientists assert that they have discovered such evidence. Are they accurately assessing evidence, or indulging in the same wishful thinking that misled Percival Lowell? The response is a topic of intense scientific discourse, yet most scientists remain doubtful regarding the purported evidence for life on Mars. Nonetheless, it is essential to scrutinize the assertions to elucidate the reasons for the scientific dispute and guide us toward future resolutions. The assertions regarding signs of life can be categorized into three primary groups: claims derived from the Viking landers' findings, claims based on methane in the Martian atmosphere, and claims stemming from analyses of Martian meteorites discovered on Earth. We will analyze the initial two groups now and reserve the topic of the Martian meteorites for later. A clear method of investigating life on Mars is to analyze the soil for the presence of live bacteria. The two Viking landers conducted the initial search in 1976. Not long ago, the term Martian was nearly equivalent. One could often encounter Martians at the local movie where they were preoccupied with invading Earth and disrupting everyone's day. The quintessential illustration of this seamless transition occurred in War of the Worlds, which generated one frightening radio drama and two relatively unsettling films. In H.G. Wells's narrative, advanced Martians relinquished their territory to seize ours. Mars was desiccating and perishing. Conversely, Earth was a planet replete with water, a refuge for our distressed friends. Nevertheless, numerous landers and rovers dispatched to Mars over the past 4 decades have revealed a barren region. No evidence exists of technologically advanced inhabitants, whether deceased or living. Hollywood, perpetually versatile, altered its methodology. Humans now travel to Mars, frequently searching for concealed evidence of habitation that would astonish astrobiologists. In the film Red Planet, our descendants strive to convert Mars into a more humane and benevolent environment to flee Earth's ecological disaster. Robotic vessels are dispatched to liquefy the polar ice caps and disseminate blue-green algae in a tenuous attempt to generate a warm, breathable environment. In these terraforming organisms, indigenous Martians resemble oversized lice. The lice consume everything from spacesuits to astronauts. It is perplexing why they have not devoured Mars. Despite its implausibility, astronauts in the space opera Mission to Mars encounter something much more unreasonable. Upon examining an unusual mountain in the Cydonia region of Mars, they uncover that it is, in fact, a colossal extraterrestrial face, obscured by dust and rock. Upon inside, the astronauts ultimately discover that the ancient Martian civilization responsible for constructing the face was annihilated by an asteroid 500 million years ago. Before vacating their planet, the Martians launched a rocket to disseminate their DNA on Earth. This molecular emigration is believed to have initiated the Cambrian explosion, marking the onset of multicellular life on Earth. One must contemplate how the Martians could possess the certainty that the jellyfish and trilobites produced from their seeding would ultimately change into people resembling the extinct Martians. Life on the Red Planet may have previously existed and possibly still does. However, our present comprehension of the Martian environment strongly indicates that any life would not have resembled hungry lice or humans. Any authentic Martians would only be discernible under a microscope. Each lander was outfitted with materials for multiple onboard robotically operated experiments, as well as a robotic arm for collecting soil samples, 8.31, for testing. The arm was capable of displacing rocks to access shaded soil that was less susceptible to sterilization by ultraviolet light from the sun. 3 tests were specifically devised to search for indications of life. A 4th experiment was devised to examine the overall composition of Martian soil. The initial biological experiment, the carbon assimilation experiment, combined a sample of Martian soil with carbon dioxide, CO2, and carbon monoxide, CO, gas delivered from Earth. In certain experimental trials, we additionally combined the dirt with water. The objective was to determine whether carbon dioxide or carbon monoxide would be assimilated into the soil, as would occur if live organisms utilized either gas as a carbon source in their metabolic processes. Carbon dioxide and carbon monoxide on Earth can be differentiated from the same gases in the Martian atmosphere due to their labeling with radioactive carbon-14, as opposed to the more prevalent stable isotope, carbon-12. The carbon absorption experiment confirmed that carbon-14 was integrated into the soil, indicating that metabolic processes were occurring. To conduct an additional test, the experiment was replicated using soil heated for 3 hours at 175 degrees Celsius, 347 degrees Fahrenheit, sufficiently elevated to disrupt the chemical bonds between carbon and other atoms, so probably exterminating any carbon-based organisms that may have existed. The soil retained the labeled carbon, suggesting that a chemical mechanism, rather than a biological one, was accountable. The second biology experiment, which focused on gas exchange, combined Martian soil with a nutrient-rich soup derived from Earth. The experiment sought to identify chemicals potentially emitted by the respiration of Martian microorganisms, including hydrogen, H2, nitrogen, N2, oxygen, O2, methane, CH4, and carbon dioxide, CO2. The preliminary results indicated the potential for life. The soil promptly emitted oxygen into the chamber following nutrient exposure. Nonetheless, additional analysis indicated chemical processes rather than biological ones. The oxygen release had traits typical of photosynthesis, yet it transpired in darkness rather than sunshine, rendering photosynthesis improbable. Furthermore, oxygen was detected even when the soil was subjected solely to water vapor instead of nutrients, which contradicted metabolic processes. Like the initial biology experiment, the reactions persisted even when the soil was subjected to temperatures that should have readily eradicated any existing organisms. The third biological experiment, the labeled release, combined Martian soil with organic nutrients. If Martian bacteria ingested nutrients labeled with radioactive carbon-14 and sulfur-35, the byproducts of their metabolism and respiration would be emitted as gases and identifiable through radioactivity. Should life exist, we would anticipate an increase in radioactivity as organisms metabolize nutrients and emit radioactive gases, followed by a stabilization as the nutrients are depleted. This is exactly what transpired. In contrast to the initial two tests, the soil heating in this experiment yielded results indicative of life. Heating the soil to 50 degrees Celsius, 122 degrees Fahrenheit, resulted in a significant loss of radioactivity. Upon heating to 160 degrees Celsius, 320 degrees Fahrenheit. No evidence of the tagged isotopes was detected in the chamber gas. The third experiment prompted a minority of scientists to speculate that Vikings discovered evidence of life on Mars. Nonetheless, most scientists remain doubtful due to the findings of a fourth experiment, the gas chromatograph/mass spectrometer experiment, that assessed the concentration of organic compounds in Martian soil. The experiment commenced by heating the soil to temperatures reaching 500 degrees Celsius, 930 degrees Fahrenheit, sufficient to exterminate any creatures, disintegrate any organic molecules present, and volatilize those molecules as gases. The gases were subjected to a gas chromatograph, which separates various gases during the passage, and subsequently examined using a mass spectrometer, an instrument that quantifies molecular masses. The findings indicated an absence of detectable organic compounds in the Martian soil. The absence of organic material seems to eliminate a biological explanation for the outcomes of the other three trials. This indicated that the ostensibly favorable outcome of the third experiment was likely attributable to a chemical process, resembling a biological consequence. Atmospheric research may yield insights regarding the possibility of life, with scientists especially captivated by the purported identification of methane in Mars' atmosphere. Methane gas cannot last for more than a few millennia in the Martian atmosphere before chemical reactions convert it into other gases. Therefore, if methane detection is authentic, Mars must possess an active source of methane gas. What are the potential sources of methane if the detections withstand additional examination? We know at least three potential causes: comet impacts, volcanic activity, or biological existence. The initial scenario is improbable, as impacts are infrequent, and a collision must have transpired relatively recently for methane to persist in the atmosphere. This results in either volcanism or life. The methane concentration in the Martian atmosphere exhibits regional variability and seasonal fluctuations. This has prompted certain scientists to prefer a biological origin. Volcanism appears plausible. The seasonal fluctuations may result from subterranean gas escape channels being obstructed in winter and unobstructed in summer. Methane has significant implications for the potential existence of life. Whether the source is volcanic or biological, the heat required for methane emission is likely adequate to sustain subterranean pockets of liquid water. This would render subsurface life more probable and undoubtedly enhance scientific interest in its active pursuit. What is our strategy for searching for life on Mars? The global scientific community has ambitious objectives for the ongoing exploration of Mars. The orbits of Earth and Mars position the two planets for closest approach around every 26 months. And scientists aspire to capitalize on each forthcoming alignment to dispatch increasingly advanced spacecraft to Mars. The successor to the highly successful Spirit and Opportunity missions is a more advanced and larger rover, Curiosity, or the Mars Science Laboratory. The launch is scheduled for late 2011, with a landing on Mars anticipated in August 2012. This robotic laboratory will collect soil and rock, drill into rocks to analyze their compositions, and conduct onboard experiments with soil and rock samples. It must also be able to detect methane gas, therefore determining the presence of an active methane source on Mars. Scientists in Boulder, Colorado, are constructing the MAVEN project for the 2013 launch window. This spacecraft will assess the gas escape from Mars's atmosphere today and should help determine the idea's validity upon rigorous examination. Neither of these missions is expected to discover life itself. Their design is to improve our comprehension of Mars's habitability, facilitating a more effective search for life. Simultaneously, because spacecraft development has been protracted, preparations are underway for forthcoming launch windows. We may conduct a sample return trip to Mars within a decade, retrieving rocks for further analysis. Considering that certain Earth species may endure in specific Martian locales, we must prevent our robotic missions from inadvertently contaminating Mars with terrestrial life. Alternatively, germs transported from Earth on a spacecraft could mislead us into thinking we have found evidence of life on Mars. The potential for contamination presents an ethical dilemma. It is feasible that terrestrial organisms could surpass indigenous Martian life, leading to extinction. Do we possess the right to undertake actions that may jeopardize indigenous life on another planet? The optimal method to circumvent these issues is to avert contamination initially. An international pact ratified in 1967 mandates that any spacecraft dispatched to Mars possess a probability of contamination lower than 1 in 1,000. Scientists endeavor to minimize contamination risks by sterilizing spacecraft before flight. Conversely, the potential for a sample return mission has generated concerns that humans may inadvertently introduce perilous Martian bacteria to Earth. Could these bacteria potentially induce diseases for which we're unprepared or outcompete terrestrial organisms in our environment? While we cannot entirely dismiss the possibility of risk, it is improbable due to the great adaptation of pathogenic bacteria to their specific host species. For instance, pathogens that affect plants typically do not infect animals. Indeed, species jumping by illnesses is infrequent and typically transpires solely between evolutionarily proximate species. HIV, the virus responsible for AIDS, is believed to have transitioned from chimpanzees to humans. Yet, on an evolutionary scale, this represents a very minor leap across distinct primate species. Consequently, even if Martian bacteria were inadvertently discharged and survived on Earth, it is improbable that they would induce disease. Moreover, as Martian meteorites routinely descend to Earth, any life concealed within Martian rocks would likely have arrived on Earth by now. The absence of observable detrimental impacts from this natural contamination suggests that Martian life is unlikely to threaten Earth's creatures. Nevertheless, given the substantial risks, practicing prudence is essential. We will bring samples from Mars in enclosed containers engineered to withstand impact during an Earth-based collision. Upon arrival on Earth, scientists will isolate them and conduct biological assessments, including exposure to terrestrial microorganisms. Biologists know about managing hazardous terrestrial bacteria, including the Ebola virus. while scientists formulate guidelines for securing potentially toxic Martian organisms. A long-standing aspiration for numerous individuals, and a component of NASA's strategy for the forthcoming decades, is to dispatch humans to Mars. Deploying individuals is significantly more challenging than deploying robots. Despite the most sophisticated rockets in preparation for the coming decades, a journey to Mars would necessitate a minimum of 3 to 4 months each way. This indicates that a human mission must convey the astronauts, their habitation, and adequate food, air, and water provisions to support the expedition. Protection against hazardous radiation is essential, necessitating the presence of an onboard storm cellar to safeguard against any severe solar flares. Furthermore, as the rockets could traverse between Earth and Mars just during their near alignment every 26 months, the astronauts would be required to remain on Mars for roughly 2 years before their return home. While it is plausible for them to obtain water from underlying ice and chemically extract oxygen from Martian water or rock, they would still require food, which must either be transported with them or dispatched separately by other spacecraft. They would also require fuel for the return voyage, which would significantly increase the mission's weight unless they could produce the fuel for the return trip on Mars, a concept currently under active investigation. Regardless of perspective, the substantial resources necessary for a human expedition guarantee that it would incur costs equivalent to numerous robotic trips while presenting significant risks to the crew. Although the expense and intrinsic risks of dispatching humans to Mars would be substantial, the scientific rewards could be considerably greater. Humans possess greater capabilities than robots, and a team of experts equipped with planetary vehicles and drilling apparatus may resolve inquiries regarding Martian life significantly sooner than robotic explorers could. Nevertheless, dispatching humans to Mars has a notable scientific disadvantage. It significantly exacerbates the challenge of preventing contamination by terrestrial creatures. Individuals serve as substantial reservoirs of germs. For instance, the quantity of bacteria present in the typical human mouth significantly exceeds the total number of individuals who have ever existed. We possess germs on our skin, in our breath, in our food, and in our waste. It would be nearly hard to prevent all these bacteria from escaping into the Martian environment during an extended sojourn. The scientific advantages and disadvantages of sending humans to Mars are evident. Nonetheless, the space program's history indicates that scientific inquiry has seldom motivated human exploration. The initiated space program commenced for political motivations, primarily as a component of a race between the United States and the Soviet Union. While yielding significant scientific data about the Moon, the Apollo program aimed to demonstrate that Americans could reach it before the Soviets. The choice to send humans to Mars will likely be influenced more by social and political factors than scientific ones. Certain individuals aspire to ultimately create permanent settlements on Mars. In summary, these colonies must function as self-sufficient ecosystems, and individuals would not risk exiting without a spacesuit. Let's consider whether we can improve the Martian environment for human habitation in the distant future. Implementing such modifications induces terraforming, as they often render the planet more analogous to Earth. Proposals for terraforming Mars aim to modify the environment to enhance atmospheric pressure and temperature. Introducing a greenhouse gas into the atmosphere may elevate the temperature. However, augmenting the pressure necessitates a greater volume of gas. A proposal entails the production of chlorofluorocarbons, CFCs, potent greenhouse gases, and their subsequent release into the Martian atmosphere. By enhancing the greenhouse effect sufficiently, elevated temperatures could liberate frozen carbon dioxide from the Martian polar caps and subsurface locations, thus augmenting air pressure and intensifying the greenhouse effect. Although oxygen would remain absent, increasing pressure could allow us to traverse Mars with merely an oxygen tank and ultraviolet radiation protection instead of a complete pressurized spacesuit. Such conditions may enable plants to thrive outside, facilitating food cultivation and augmenting air oxygen levels. The concept may be viable, although its execution would prove challenging. Sunlight degrades CFCs, necessitating their constant and substantial production to promote greenhouse warming. Calculations indicate that a manufacturing capacity approximately 1 million times greater than our recent CFC production capability on Earth is required, and it must be sustained for several 100,000 years, until the surface temperature increases sufficiently to release significant amounts of carbon dioxide into the atmosphere. Therefore, we have ample time to contemplate the ethical implications of terraforming, which may be substantial if Mars possesses life. Do we possess the right to modify a planet in a manner that could jeopardize its indigenous life forms? Notably, science fiction authors examined many ethical dilemmas associated with Mars colonization long before the concept of terraforming emerged. Historically, when belief in canals and a moribund Martian society prevailed, numerous narratives explored the circumstances under which humanity may occupy Mars. For our final commentary on human colonization, we reference the science fiction narrative The Million-Year Picnic, authored by Ray Bradbury in 1946, and featured in his compilation The Martian Chronicles. The narrative recounts the journey of a human family that flees to Mars as humanity on Earth culminates its civilization through animosity and conflict. The family discovers abundant water and the deserted towns abandoned by extinct Martians on Mars. The narrative concludes with the family beside a canal, where one of the children inquires of his father on a previously stated commitment. "I have always desired to encounter a Martian," stated Michael. "Where are they, father?" "You made a pledge." "There they are," replied Dad, adjusting Michael on his shoulder and pointing directly downward. The Martians were present. Timothy started to tremble. The Martians were present. In the canal mirrored in the water, Timothy, Michael, Robert, mother and father. The Martians gazed back at them for an extended, silent duration from the undulating sea. As previously mentioned, one piece of evidence for life on Mars is from examining Martian meteorites that have landed on Earth. The narrative commenced in 1984 when a group of American scientists retrieved a 1.9 kilogram meteorite from the Allen Hills area of Antarctica. It was designated as ALH 84001. ALH for Allen Hills, 84 for the year of its discovery, and 001 to signify that it was the inaugural meteorite located during the trip. Initially, it did not attract any attention. Nevertheless, a decade later, examination revealed it to be a rare meteorite from Mars. It subsequently demonstrated its uniqueness even within this limited collection of rocks and underwent rigorous examination. In 1996, a team of experts led by David McKay at NASA asserted that ALH 84001 contains fossil evidence of former life on Mars. This chapter employs this assertion as a case study of scientific practice due to its contentious nature and significance if validated. Is there proof of life in Martian meteorites? To assess the assertions of ALH 84001, we must first comprehend the rock. Scientists are reasonably confident, but with some reservations that ALH 84001 is a Martian meteorite. This is unequivocally not an Earth rock, as the relative abundances of the isotopes oxygen-16, oxygen-17 and oxygen-18 differ markedly from those in terrestrial rocks. However, it also does not conform to our expectations for a fragment of an asteroid or a lunar rock. The gas contained within ALH 84001 exhibits a chemical and isotopic composition closely resembling Mars's atmosphere. It significantly differs from all known gas sources in our solar system, leading scientists to hypothesize that it originated from Mars. Researchers concentrated more rigorously on ALH 84001 than other Martian meteorites for a specific reason. In contrast to other recognized Martian geologically recent meteorites, radiometric dating revealed that AL-H84001 is an igneous rock that solidified approximately 4.1 billion years ago. Consequently, it originated approximately 400 million years after the formation of Mars, indicating its presence on Mars when liquid water traversed the surface. Consequently, scientists speculated whether it could provide insights into Mars's historical habitability. A thorough examination reveals significant insights into the history of AL-H84001. Radiometric dating determines its age, whereas structural analysis provides evidence of subsequent shocks, likely resulting from impacts occurring long before the event that eventually propelled it into space. The meteorite contains carbonate grains of around 0.1 to 0.2 millimeters in diameter. These grains date back around 3.9 billion years and indicate that the rock was likely in contact with liquid water. The formation of carbonate crystals atop the rock substantiates the hypothesis that Mars once possessed flowing water. We can determine the timing of the impact that propelled AL-H84001 into orbit by examining indicators of exposure to cosmic rays. These are high-energy particles that impart chemical signatures on objects without an atmosphere. The findings indicate that AL-H84001 traversed space for approximately 16 million years, suggesting that the impact initiating its voyage transpired on Mars around 16 million years ago. By analyzing decay products from radioactive isotopes generated by cosmic rays, we ascertain the moment cosmic rays ceased to affect the meteorite, which coincides with its descent to Earth and subsequent shielding by the atmosphere. This research indicates that AL-H84001 arrived in Antarctica approximately 13,000 years ago. Table 8.2 encapsulates the chronology of AL-H84001. The purported evidence of life in AL-H84001 is derived from comprehensive analyses of its carbonate grains and the adjacent rock. Researchers have identified 4 categories of evidence indicating the presence of biological activity on Mars. The carbonate grains exhibit a stratified structure with alternating layers of magnesium-rich, iron-rich, and calcium-rich carbonates. This form of layering on Earth often arises solely from biological activity. Carbonate granules comprise intricate chemical compounds called polycyclic aromatic hydrocarbons, PAHs. Both biological and abiotic activities can generate these compounds. Numerous meteorites not originating from Mars do contain these compounds. However, they have a significantly higher concentration in AL-H84001 than other meteorites. On Earth, these molecules are typically generated via the decomposition of deceased creatures, or by environmental reactions with decay byproducts, such as the combustion of fossil fuels. Under a microscope, crystalline magnetite crystals are observed within the iron-rich layers of carbonate grains. These crystals' dimensions, configurations, and orientations correspond to those of magnetite grains that exclusively form on Earth by bacterial activity, 8.33. Notably, highly magnified photographs of the carbonate grains exhibit rod-shaped features like petrified bacteria, albeit significantly smaller. Although none of these pieces of evidence independently substantiate biological activity, the initial researchers contended that collectively, biological activities appeared to be a significantly more plausible explanation than abiotic mechanisms. Utilizing Occam's razor, they suggested that it would be simpler and therefore superior for science to account for all phenomena through a singular process, biology, rather than necessitating distinct processes for each outcome. The 4 lines of evidence for fossilized life in AL-H84001 support a compelling argument for the existence of previous life on Mars. Nevertheless, some scientists have suggested alternate non-biological explanations that could account for each observed occurrence. we will examine these possibilities in the same sequence in which the evidence was presented. Non-biological methods may exist for producing layered carbonate. For instance, many pulses of heated water containing various dissolved elements may have traversed the rock, depositing mineral strata. Other meteorites demonstrate that PAHs can originate from chemical processes rather than biological ones, and their elevated abundance may also be attributed to terrestrial contamination, while the rock was in Antarctica. Certain experts contend that the magnetite crystals and chains within the meteorite were created abiotically, notwithstanding their physical resemblance to Earth's microbes. The rod-shaped entities may resemble bacteria, but are approximately 100 times smaller than conventional terrestrial bacteria. They are so diminutive, merely 10 to 20 nanometers in width, that it is challenging to comprehend how the intricate molecules purportedly requisite for life, such as RNA or DNA-like molecules, may be accommodated within them. Subsequent meteorite analysis disclosed the existence of contemporary terrestrial microorganisms, suggesting that life from Earth has contaminated it. Although this revelation is not particularly unexpected in hindsight, given that the meteorite resided in Antarctica for 13,000 years before scientists discovered it, it undeniably complicates the differentiation between biological molecules originating from Mars and those potentially produced on Earth. The discourse on potential evidence of life in ALH 84001 persists. However, the majority of scientists currently favor non-biological interpretations of the findings. Nonetheless, the discourse has imparted two essential truths pertinent to the quest for life on Mars. It now appears improbable that a meteorite discovered on Earth can definitively demonstrate the existence of life on Mars. Rather, it is essential to examine Martian rocks directly, or retrieve samples from Mars for analysis on Earth. Secondly, although meteorites are improbable sources of life information, they can provide significant insights into the historical conditions on Mars. The historical evidence presented in ALH 84001 substantiates the hypothesis that Mars originally possessed water, thermal sources, and potentially organic life on Jovian moons. Jupiter orbits the Sun at more than 5 times Earth's distance, and the other Jovian planets, Saturn, Uranus, and Neptune, lie much farther from the Sun. Sunlight in this distant realm is faint, too weak to provide warmth. Nevertheless, several moons in our solar system's frigid outer reaches are now considered possible places to find life beyond Earth. In this chapter, we will investigate these distant worlds. We'll examine these moons' fundamental characteristics and why some may have liquid water. We'll then turn our attention to the most promising potential abodes of life, including Jupiter's moons Europa, Ganymede, and Callisto, and Saturn's remarkable moon Titan, which is blanketed by an atmosphere thicker and denser than Earth's. The sirens of Titan drew me in, their call carrying me along as I sought enlightenment and the meaning of it all. The wind threw me to the stars like a kiss. The sirens of Titan drew me in, as they do for all of us, as are we all. Al Stewart, from his song Sirens of Titan, based on the Kurt Vonnegut novel. Aside from addressing our general curiosity about the habitability of Jovian moons, our discussion in this chapter will lead to an intriguing possibility. It's conceivable that these cold and distant moons could be the most numerous homes to life in our solar system. If any of these moons harbor life, the possibilities for discovering biology elsewhere in the universe will greatly expand. The moons of the outer solar system, the Jovian planets themselves, seem unlikely to be habitable. However, numerous moons, known as Jovian moons, orbit these planets. The idea of finding life in the cold outer solar system once seemed far-fetched, but several Jovian moons now seem potentially habitable. In this section, we'll introduce the major moons and explore the mechanisms that make it possible for at least some of them to have liquid water or other liquids on or within them, thus creating possible habitats for life. What are the general characteristics of the Jovian moons? As of early 2010, the 4 Jovian planets were known to have at least 165 moons among them. A few of the larger of these moons have been known to astronomers for nearly 4 centuries, but many of the smaller ones have been found only with the improved telescopes and space probes of the last few decades. Probes, in particular, have given us the chance to study these worlds from close by. While previous generations knew Jovian moons only as points of light, today, many photographs show enough detail to name individual craters and other features. One of the biggest surprises emerging from our modern reconnaissance of these moons is learning that some might be potential homes to life. Discovering the moons. Among Galileo's many discoveries, one of the most notable was finding the 4 large moons of Jupiter. Having heard of the telescope's recent invention, Galileo built his homemade versions beginning in 1609. At the time, the telescope was thought to be primarily a toy, or possibly useful for defense. Galileo, however, did something different with his telescopes. He turned them toward the sky. On January 7th, 1610, while gazing at Jupiter, he saw what at first seemed to be 3 small stars in its vicinity. What intrigued Galileo was that the 3 were close to one another and in a line. The following night, he looked again and was surprised to note that the 3 stars had moved relative to Jupiter, but not in the direction or to the extent expected of stars. A few days later, he noticed a 4th point of light, and within a week, he understood that these 4 stars consistently remained near Jupiter and were unmistakably in orbit around it. In March 1610, Galileo published his results in the Starry Messenger pamphlet, claiming to have found 4 bodies moving around the giant planet, as Venus and Mercury around the Sun. These 4 bodies are what we now call the Galilean moons of Jupiter. Proceeding outward from that planet, we know them individually as Io, Europa, Ganymede, and Callisto. Other scientists soon discovered additional moons in the outer solar system. The accomplished Dutch scientist Christian Huygens, 1629 to 1695, found the largest of Saturn's moons, Titan, in 1656. Before the close of the 17th century, Giovanni Domenico Cassini, 1625 to 1712, an Italian astronomer who became director of the Paris Observatory, had discovered 4 more moons around the ringed planet. Astronomers continue to discover moons orbiting the Jovian planets even today, despite having undoubtedly discovered all of the larger moons by now. The new discoveries involve small moons, usually no more than a few kilometers across, detected with new telescopes or spacecraft. Size and orbits of the moons. The Jovian moons come in a wide range of sizes. While many small ones are smaller than a single mountain on Earth, others are much larger. The 2 largest, Jupiter's moon, Ganymede, and Saturn's moon, Titan, are bigger than the planet Mercury. The 3 other Galilean moons, Io, Europa, and Callisto, and Neptune's moon, Triton, are bigger than Pluto, a montage of Jovian moons larger than about 350 kilometers in diameter. Almost all the moderate and large-size moons orbit their planets like planets orbit the Sun. They orbit nearly in the equatorial plane of their host world, moving in the same direction as their planets spin. In this sense, they resemble miniature solar systems, which suggests that they were formed in a smaller-scale version of the same processes that gave birth to the planet. The gravity of the Jovian planets drew in gas and dust from the surrounding solar nebula. Like the solar nebula, this gas and dust formed a swirling disc-shaped cloud around each Jovian planet. Condensation and accretion then built moons that shared the orbital properties of the original disks of gas and dust. The small Jovian moons differ from their larger brethren in appearance and their orbit's properties. Most are irregular and resemble peanuts, potatoes, or other snack foods. This is hardly surprising. These small objects' weaker gravity prevents the rigid material that makes them into spheres from forming. Some small moons may have formed in place, like most of the larger moons, and others come in groups that share common orbital characteristics, suggesting that they may be fragments of larger moons that broke apart. However, many of the smaller moons also have orbits that are highly elliptical, or inclined to the equator of their host planet. In some cases, the moons orbit backward relative to their host planet's spin. These orbital characteristics indicate captured asteroids or comets, likely beginning their independent orbit around the Sun, as we discussed briefly in section 4.6. It's not easy for a planet's gravity to grab a wayward asteroid or comet. Because energy must be conserved, the passing object must somehow lose some of its orbital energy, or else it would simply fly on by and continue its path around the Sun. The most popular theory says that captures happened when the Jovian planets were young and had thick, long-lasting atmospheres that could have slowed down small bodies as they passed close by, taking away their orbital energy and letting them be captured. Moreover, one large moon exhibits orbital characteristics that indicate it is a captured object. Neptune's moon, Triton, orbits backward relative to its planet's rotation. This orbit makes it a near certainty that Triton once orbited the Sun as an independent object. However, capturing such a large object poses a trickier problem than capturing smaller moons. Recent research indicates that the satellite could have captured Triton if it had previously orbited it. Since the satellite was ejected from its orbit, Triton's excess orbital energy could have been carried off and snagged while passing near Neptune. Regardless of the specific mechanism of the capture, for several decades, scientists have assumed that Triton was once one of the Kuiper Belt objects, KBOs, of which we now consider Pluto a member. Indeed, the fact that Triton is larger than Pluto is one reason why some astronomers suspected that Pluto might not be the largest such object in the outer solar system. A suspicion confirmed with the 2005 discovery of Eris, an ice-rich world that is larger than Pluto, and nearly 100 times as far from the Sun as Earth. Composition of the moons. As discussed in Chapter 3, the outer solar system was cold enough to allow ice to condense with metal and rock. As we expect, most of the Jovian moons are ice and rock. The average densities of most Jovian moons are significantly lower than that of Earth, reflecting the fact that they contain substantial quantities of ice, which is low in density. Within individual moon systems, we see variations in composition reflecting that the moons formed at different distances from a hotter central planet. For example, the Galilean moons show a decrease in density with distance from Jupiter, just as we would expect if they formed from a swirling cloud of gas, hotter in the center than in its outer regions. Io's density indicates that it has virtually no water in any phase. Europa is mostly rock with water ice, and perhaps a liquid ocean, only in its outer layers, and Ganymede and Callisto have more significant amounts of water ice relative to their amounts of rock. In addition to the compositional variation within individual moon systems, there is variation in the composition of moons as we move from one planet to the next. These differences came about because of temperature differences in the overall solar nebula. Water ice condensed easily at the temperatures near Jupiter's orbit, but methane and other ice condensed only at the colder temperatures at significantly greater distances from the Sun. As a result, Jupiter's moons contain significant quantities of water ice, but only a smattering of other ice. Moons of distant planets contain higher proportions of ice than rock, containing water, ice, methane, and other ices. Synchronous rotation of the moons. Nearly all Jovian moons share a common characteristic. They always turn the same face toward their planet, like our moon. This behavior, called synchronous rotation, means that each moon completes exactly one rotation around its axis, while it makes one orbit around the planet. You can see how this works with a simple demonstration. Place a ball on a table representing a planet like Earth, and walk around the ball so that your head represents an orbiting moon. Without rotating, you'll face away from the ball halfway around your orbit. You can only face the ball at all times by completing exactly one rotation while you complete one orbit. Synchronous rotation is not a coincidence. Rather, it develops naturally due to the same gravitational effects that lead to tides on Earth. Recall that the strength of gravity declines with distance, following an inverse square law, section 2.4. As a result, the Moon's gravitational pull on the near side of Earth is slightly stronger than that on the far side. This difference in the strength of gravity is the cause of the tides. Note that there are two tidal bulges, one facing the Moon and one opposite, which is why there are two high tides per day as Earth rotates through the bulges. Simply put, there are two bulges because the oceans on the side nearest to the Moon are being pulled away from Earth, while the oceans on the opposite side bulge because Earth is being pulled away from under them. A better way to look at tides is to recognize that the gravitational attraction toward the Moon gets progressively weaker with distance throughout Earth. This varying traction stretches the entire Earth, land and ocean, along the Earth-Moon line. The tidal bulges are more noticeable for the ocean than the land because liquids flow more readily than solids. Recall that solids can flow, though slowly, which is why Earth's solid mantle can undergo convection. Because tidal forces stretch Earth itself, the process necessarily creates tidal friction. As this tidal friction has important consequences for Earth and the Moon, because it allows Earth's rotation to pull the bulges slightly ahead of the Earth-Moon line. This slight misalignment of the tidal bulges with the Earth-Moon line means the Moon's gravity is always pulling back on the bulges, causing. A planet's tidal force on a satellite is the difference between the gravitational force on that satellite's near and far sides. One way to understand this difference is to consider a test mass, a 1 kilogram rock, on the satellite's surface. If d is the distance between the center of the planet and the center of a satellite of radius rsat, then on the near side of the satellite, the distance from the planet's center to the 1 kilogram rock is d minus rsat, and on the far side it is d plus rsat. We then calculate the gravitational force in both positions and subtract it to get the tidal force acting on the satellite per kilogram of mass. Earth's rotation is to slow gradually. At the same time, the gravity of the bulges pulls the Moon slightly ahead in its orbit, causing the Moon to move gradually farther from Earth. These effects are barely noticeable on human time scales. The Moon is moving farther from Earth at only about 4 centimeters per year, as measured by laser beams bounced off the lunar surface, and tidal friction increases the length of Earth's day by only about 1 second every 50,000 years. On short timescales, this effect is overwhelmed by other effects on Earth's rotation. But the effects add up over billions of years. Early in Earth's history, a day may have been only 5 or 6 hours long, and the Moon may have been 1/10 or less its current distance from Earth. By reversing the situation, we can comprehend the Moon's synchronous rotation. Just as the Moon raises tides on Earth, Earth must raise tides on the Moon. In fact, much stronger tides, because Earth's gravity is much stronger than the Moon's. If the Moon rotated rapidly, these tides would generate substantial tidal friction that would slow the Moon's rotation. The tidal friction would cause the Moon's rotation to slow until it always kept the same face as Earth. No matter how fast the Moon rotated at its birth, tidal friction would slow it until it was synchronous. At that point, the synchronous rotation was permanently locked in, because there was no more tidal friction to further slow the Moon's spin. Tidal friction similarly explains the synchronous rotation of the Jovian moons. From the time of its birth, when a moon was rotating faster than it orbited, tidal friction slowed its rotation until the rotation and the orbit were synchronized. Given the large sizes of the Jovian planets compared with their moons, synchronous rotation likely set in for the close-in moons within no more than a few million years. Why do we think that some moons could harbour life? Most of the Jovian moons are almost certainly lifeless. As discussed in Chapter 7, they are too small and too far from the Sun to have any reasonable likelihood of having liquid water or other liquids. However, the situation may differ for a few bigger moons. One large moon, Titan, appears to have a temperature and atmospheric pressure that sometimes allows liquid methane and ethane to form lakes or rivers on its surface. In addition, several moons may have enough internal heat to keep water liquid in their interiors, making them potentially habitable. Tidal heating. Based on what we've learned about internal heat on the terrestrial planets, it might seem surprising to find much internal heat in any of the Jovian moons. After all, only Ganymede and Titan are even as large as Mercury. And we know that Mercury's interior has cooled enough over time that it no longer supports active volcanism. But when the Voyager 1 spacecraft passed Jupiter in 1979, we got definitive proof that at least some distant moons have plenty of internal heat. Confirming a theoretical prediction made just weeks before Voyager's arrival, the spacecraft photographed active volcanic eruptions on Io, the innermost of the 4 Galilean moons. The Galileo orbiter then provided much more detailed views. How did scientists predict this surprising volcanism? They realized that Jovian moons could have internal heating different from that found in the terrestrial worlds, and that I would be an extreme example of this heating. Recall that Earth and the other terrestrial worlds were all hot inside at birth, with heat from accretion, differentiation, and radioactive decay, section 4.4. Over time, heat has escaped and only radioactive decay continues to supply new heat. In small worlds, like the Moon and Mercury, the supply of new heat has not been enough to overcome the heat lost by escape. If these same sources were all that could heat the Jovian moons, they would be cool by now too. To explain the internal heating of Io, we must consider a different process. Scientists call this tidal heating because it arises from the effects of tidal forces. Io's tidal heating arises from a combination of 2 factors. 1. Its proximity to Jupiter means it experiences a strong tidal force from the massive planet. And 2. Io has a slightly elliptical orbit, which causes the strength and direction of the tidal force to change somewhat as Io moves through each orbit. The constantly changing orientation of Io's tidal bulges means that Io is continuously being stretched in different directions, which generates friction inside it, in much the same way that stretching warms silly putty. Tidal heating generates tremendous heat on Io, more than 200 times as much heat per gram of mass, as the radioactive heat driving much of Earth's geology. This heat makes Io the most volcanically active place in the solar system. Material from Io's volcanic vents reaches temperatures of more than 1,000 degrees Celsius, 1,800 degrees Fahrenheit. And eruptions often spew plumes of sulfur and other gases to heights of hundreds of kilometers. Although the combination of the elliptical orbit and Jupiter's tidal force seems to explain tidal heating, there is another question. Why is Io's orbit slightly elliptical when most large satellites have nearly circular orbits? The answer lies with an orbital resonance that occurs among Io, Europa, and Ganymede. The 3 moons periodically line up because during the time Ganymede takes to complete one orbit of Jupiter, about 7 days, Europa completes 2 orbits, and Io completes 4 orbits. The effect is much like that of pushing a child on a swing. If timed properly, a series of small pushes can add up to a resonance that causes the child to swing quite high. For the 3 moons, the periodic alignments mean they experience repeated gravitational tugs that act much like the child's repeated pushing on the swing, hence the term orbital resonance. In this case, these gravitational tugs cause the orbits to be more elliptical than they would be otherwise. Like synchronous rotation, we expect orbital resonances to arise quite naturally. The orbital resonances of Io, Europa, and Ganymede probably came about because of feedback from the tides that the moons raise on Jupiter. Just as our moon raises tides on Earth that are gradually causing the moon to move farther from Earth and slowing Earth's rotation, the Galilean moons also raise tides in Jupiter's atmosphere that cause the moons to move farther from Jupiter. The effect is greatest on the closest in moon, Io. So we might expect that its orbit should have tended to move outward until it achieved resonance with the next moon out, Europa. Then Io and Europa could have continued moving outward in lockstep until they reached a resonance with the third moon, Ganymede. This may be how Io, Europa, and Ganymede came to have orbital resonances among themselves. Indeed, these moons may now be moving slowly outward, in lockstep toward Callisto, though it will be many billions of years before they could reach a resonance with this fourth moon. Other heat sources. Tidal heating explains Io's volcanic activity and Europa's internal heat. As we'll see in the next two sections, however, it may not be enough to explain the heating that apparently occurs or has occurred in the past on a few other Jovian moons. Saturn's moon Iapetus, for example, has a striking equatorial bulge that indicates it must once have been warm enough to be soft inside. But tidal heating does not seem to explain how it became hot enough for its interior to become sufficiently plastic to flow. One possible explanation lies with radioactive decay. If Iapetus and other moons could have incorporated enough short-lived radioactive material during their formation to explain the level of heating that they have apparently experienced. Life on Jupiter's Galilean moons. Tidal heating has turned Io into a veritable hell, and its lack of water and extreme volcanic activity essentially rule it out as a home for life. However, tidal heating has lesser effects on Europa and Ganymede, and no effect on Callisto, because it does not participate in the orbital resonance. In the case of Europa, the tidal heating level may be just right for life. Without tidal heating, Europa would be wrapped in solid ice. However, its appearance and other characteristics hint that this moon has a subsurface ocean, making it a possible home to life. This section will discuss the prospects of habitability and life on Europa, and the prospects for the outer two Galilean moons, Ganymede and Callisto. Does Europa have an ocean? Scientists already knew that an icy shell covered Europa before the Voyager spacecraft took the first detailed photos of the planet in 1979. Spectroscopic observations from Earth indicated the presence of water ice on the surface, although the amount was unknown. Based on our ideas about the formation of moons, theoretical studies suggested that Europa was likely built of a mixture of rock and water. If heat had caused the moon to differentiate sometime in the past, the less dense water would have migrated to the surface. The Voyager spacecraft confirmed at least part of this speculation. Europa's exterior is bright white and ice-covered. Also, its surface is remarkably smooth with few features rising above a kilometer. Faint ridge lines, giant cracks in the ice, crisscross the surface, looking almost like a spider web of highways. The Galileo orbiter revealed Europa in much more detail. The small number of recognizable impact craters indicates that recent geologic times have repaved Europa's surface. However, it is difficult to tell whether the resurfacing has been caused by the action of liquid water or ice that is relatively warm, and, therefore, soft enough to flow, as glaciers flow on Earth. Scientists could determine its internal layering using the Galileo spacecraft to measure subtle variations in Europa's gravitational field. Crudely speaking, Europa seems to consist of a central metallic, probably iron, core, overlaid with a thick mantle of silicate rock, and an 80 to 170 kilometer thick outer skin of water or water ice. From the gravity measurements alone, the water layer could contain just about any combination of solid ice, liquid water, or slush, partially melted ice, because all of these have about the same density, 11 grams per cubic centimeter. As a result, over the past couple of decades, scientists have debated which form of water is most likely. The debate is not yet fully settled. But as we'll discuss shortly, a careful analysis of data from the Galileo spacecraft suggests that the most likely answer is that Europa probably has a brittle, icy crust underlaid by a layer of warmer ice that can flow easily. It undergoes convection with a liquid water ocean beneath it. Surface temperatures on Europa are brutally cold, typically minus 150 degrees Celsius squared. So the top portion of its icy crust must be as stiff as granite. Evidence for a liquid ocean. The spacecraft pictures prove that liquid water, not just more ice, underlies Europa's frozen skin. One key piece of evidence comes from the surprising lack of impact craters. Europa has only a few dozen large craters, 10 kilometers or more across, a number that should accumulate in only a few tens of millions of years, not the billions of years since the solar system's formation. Clearly, something has erased the craters on Europa. An obvious candidate is resurfacing caused by an occasional subsurface water or slushy ice breakthrough. Another suggestive evidence is the appearance of Europa's so-called chaotic terrain, which resembles photos of an Arctic ice pack. The surface is clogged with iceberg-like blocks, some as small as football fields and others as large as a city, crisscrossed by ridgelines and suspended in what appears to have been a slushy ocean that froze. Often these blocks appear to have rafted away from their original positions. Imagine placing your palms on an assembled jigsaw puzzle and spreading them slightly. Gaps will form between the pieces, and the picture printed will become disjointed. Europa's ridgelines similarly form a telltale picture on the ice, a picture that in places has fractured into small, jostled pieces. The eye can trace individual ridges from one block to another, demonstrating the motion that must have occurred. Further evidence for an ocean comes from features suggesting that liquid water has gushed from below and frozen in spaces between some of the ridges. Although the photographic evidence suggests that an underlying ocean has churned Europa's ice pack interior, it still raises doubts. Could the ocean that produced the tortured and broken surface exist millions of years ago and is now frozen, meaning that Europa's intriguing face is merely the remnant of an earlier time? Perhaps the icy crust sits atop relatively warm, soft or slushy ice, and the surface features result from this warm ice convecting upward from below and melting pockets of ice within the crust. In that case, Europa's frigid skin might extend to the Moon's rocky interior. But another line of evidence, arguably even more convincing than the photos, makes the case for a liquid ocean. In 1996, a magnetometer aboard the Galileo spacecraft detected a magnetic field near Europa. Because moons seldom have a magnetic field, though, as we'll discuss shortly, Ganymede does, researchers asked themselves what was causing magnetism on Europa. Jupiter has a strong magnetic field, which causes it to be a relatively powerful source of natural radiostatic, and Europa orbits within this field. Jupiter's magnetic equator tilts about Europa's orbit, causing its field at Europa's position to constantly change as the giant planet spins on its axis. Just as a moving magnet produces an electric current in a coil of wire, so too could Jupiter's changing field induce currents in an electrical conductor within Europa. Of course, there's no giant coil of wire in Europa, but a salty ocean would conduct electricity much the same way. The currents in such an electrically conducting ocean would act to set up a magnetic field that opposed Jupiter's, and thus would change as Jupiter's field changed. Additional measurements with Galileo's magnetometer showed that Europa's magnetic field changes as Jupiter spins. Most researchers consider this the best evidence that a liquid, salty ocean exists under Europa's icy surface. The magnetometer data require that Europa's subsurface water be global in extent, not limited to just a few isolated liquid pockets. They also imply that this ocean could be as salty as Earth's seas. Some of Galileo's instruments also found evidence for what appeared to be salt on Europa's surface, possible seepage from the briny deep. If we tally up the evidence for an ocean on Europa, we can list the following. Calculations show that tidal heating can supply enough heat to keep most of Europa's ice melted beneath a solid ice crust. The relatively small number of craters implies that the Moon's surface is young, perhaps only a few tens of millions of years old, indicating that it has been recently repaved. Various features on the surface, chaotic and flooded terrain, suggest that liquid water sometimes wells up from below. Currents produced in anything that conducts electricity, like a salty ocean, likely cause Europa's magnetic field to change, as Jupiter's magnetic field does. While no single piece of evidence would make an overwhelmingly strong case by itself, the evidence gives us sufficient reason to suspect that it is correct and that a liquid ocean exists beneath Europa's surface. Still, the case is not definitive. For that, we'll need new space missions. Proving the case for an ocean. NASA scientists hope to send an orbiter to Europa, equipped with instruments that include a laser altimeter and long-wavelength radar. NASA would use the altimeter to search for evidence of an ocean beneath the ice. Europa's gravitational tug-of-war every 3.6 days in its elliptical path around Jupiter causes distortions in its shape. Europa's surface will regularly bulge in and out by up to 30 meters if a deep, liquid ocean exists under the ice. However, if there is only solid ice beneath the surface, Europa won't stretch so easily, and the altitude change in the bulge will be only about 1 meter. The altimeter can reliably measure the altitude change, thereby resolving the debate about the existence of the ocean. The radar can also probe the icy crust, looking for radio reflections from a subsurface water interface. This same technique was used in Antarctica to discover a lake, Lake Vostok, that lies hidden beneath a 4-kilometer thick deck of ice. If there is an ocean on Europa, how big might it be? The current model suggests that the frozen crust, including the region of warmer convecting ice, is about 20 to 25 kilometers thick. Given that our models of Europa's interior indicate that the total thickness of the water ice layer is between about 80 and 170 kilometers, a 20 to 25 kilometer thick crust leaves plenty of room for a deep ocean. In fact, if a global subsurface ocean exists, it could easily be 100 kilometers or more deep, some 10 times as deep as the deepest ocean trenches on Earth. A 6 kilometer meli Europai, Ocean Körülbelül, 4 anni vistartalmasna minda föld tengerenek együtese. Could Europa have life? The oceans on Earth teem with life, and in Chapter 6 we discussed reasons why many scientists suspect that life on Earth first arose in the oceans, most likely near deep-sea volcanic vents. If Europa had a deep ocean, tidal heating would have probably kept it liquid for billions of years. Might life have arisen in the European ocean as it arose on Earth? And could Europa be home to life today? We identified the 3 key environmental requirements for life. 1. A source of elements and molecules from which to build living organisms. 2. A source of energy for metabolism and growth. And 3. A liquid medium for transporting the molecules of life. If Europa has an ocean, then it clearly meets the 3rd requirement. As discussed in Chapter 7, nearly all worlds probably contain some quantity of the 25 elements that make up life on Earth. Europa is probably no exception. Its rock-water composition likely has all these elements, satisfying the 1st requirement. These elements are likely present at the ocean floor's rock-water boundary, where life may have originated. That leaves the question of whether Europa satisfies the 2nd requirement. Does it have an energy source for life? You might at first guess that the existence of a liquid water ocean would automatically mean there is life energy. After all, if there is liquid water, there must be enough energy from tidal heating and radioactive decay to keep the water temperature above freezing. However, the energy generated by heated water is insufficient to sustain life. That is why fish can't live off ocean heat alone. In general, extracting energy from a reservoir of warm water is possible only if there is an adjacent sink of much colder water and a substantial difference in temperature between the two. While we can build machines to take advantage of such temperature differences, life has an additional requirement. Chemicals that can react to generate energy for biological use must be present. In practice, this additional requirement is almost certainly met when we have temperature differences at a rock-water boundary, because molecules in the rock and water can react in various useful ways. Thus, to decide whether there might be life in a European ocean, we must ask whether there is enough energy in a useful form to support biology. We can separate this question into two parts. First, is there enough energy to support the origin of life? Second, is there enough energy to support a reasonable total biomass for ongoing life? Let's begin by considering the question of energy for the origin of life. Energy for an origin of life. From an energy standpoint, the possibility that life on Earth might have begun near deep-sea vents makes sense. The volcanic vents heat the water near them to very high temperatures, creating a large temperature difference with the surrounding cooler water. This temperature difference facilitated chemical reactions between the water and the rock that erupted from the vents, forming complex organic molecules and perhaps the origin of life. Therefore, we may wonder whether the same type of vents exist on Europa, providing the energy needed for the origin of life. We cannot see through Europa's icy crust, so we don't know that a liquid ocean lies beneath it. We cannot know whether Europa has volcanic activity on an ocean floor. Nevertheless, the possibility of volcanic vents seems reasonable. Our models of Europa's interior suggest that it should have a rocky ocean floor, and tidal heating and the decay of radioactive elements may provide enough energy to melt pockets of interior rock that could erupt into the ocean. Europa might even have large undersea volcanoes. In that case, imagining an independent origin of life on Europa certainly seems plausible. Energy to support ongoing life. If life did arise in a European ocean, how widespread could it be today? While deep-sea vents might lead to enough energy for an origin of life, they could not support more than a small total biomass because they don't make enough energy available to organisms. This fact might surprise you if you think about the enormous communities of life that live near deep-sea vents on Earth today. But most of this life actually gets its energy from materials that filter down from above, such as dead organisms and oxygen produced by photosynthetic life near the surface. Only a small fraction of the life near Earth's deep-sea vents lives solely off the vents' energy. Thus, for life to be similarly abundant or widespread in Europa, it would need some other energy source besides chemical reactions near deep-sea vents. On Earth, sunlight is the best-known energy source for life, as photosynthesis converts it to energy that works its way up the food chain. Sunlight cannot penetrate through more than a few tens of meters of ice, so it could not directly provide energy for life in a European ocean. However, if pockets of liquid water exist near the top of the ice crust, then photosynthesis might provide energy to organisms living in these pockets, and this energy might then filter downward as organisms, dead or alive, cycle between the crust and the ocean. Even in this case, however, remember that because Europa is about 5 times as far from the Sun as Earth, sunlight is about 52 equals 25 times weaker at Europa than at Earth. Overall, photosynthesis seems unlikely to play any role in Europa, and in the best case, it could support only a much smaller abundance of life than it supports on Earth. Before the origin of photosynthesis on Earth, biochemical reactions may have been facilitated by energy sources such as lightning, ultraviolet radiation from the sun, and heat released by impacts from asteroids and comets. Unfortunately, none of these energy sources will likely be useful for life in the Mediterranean seas. Europa has no atmosphere for lightning, ultraviolet light does not penetrate the ice, and the time during which impacts were frequent enough to provide significant energy ended some 4 billion years ago. However, another possible scheme for producing energy on Europa's icy surface exists. High-energy particles accelerated and trapped in Jupiter's magnetic field, and ultraviolet light from the sun regularly slam into the surface ice. When these particles and photons hit the surface, they have enough power to break up molecules in the ice. This makes small amounts of other molecules, like hydrogen peroxide, 1H2O2, molecular oxygen, 1O2, and hydrogen, which quickly escapes. Europa has a very thin atmosphere which you can't see but can be measured. These molecules can help reactions that make energy, and the small meteorites that hit Europe often should mix them into the top layer of the continent's surface. If all these molecules were ultimately in the ocean below, they could provide energy to support life there. Unfortunately, we don't know how much outer ice gets cycled into the water below, or how often. In addition, the total amount of energy that might be available in this way is at least 10,000 times less than the amount of energy that photosynthesis generates on Earth, so an ocean on Europa could not support anywhere near as much life as the oceans on our planet. One other known process might yield some energy for life on Europa. The ocean would dissolve potassium in the rocky material of this moon, then freeze in the ice above. The energy from the natural decay of one of potassium's radioactive isotopes would produce both hydrogen and oxygen molecules. Rough estimates suggest these molecules could facilitate chemical reactions supporting a small biomass. The case for possible life on Europa. Summarizing the case for life on Europa, we can say, there is strong indirect evidence that a liquid water ocean exists. We expect the elements needed for life to be present in that ocean and on its floor. There are possible energy sources to support life, but the total available energy is small compared to the energy available for life on Earth. The evidence makes Europa seem like a worthy candidate for the possibility of life. That said, we should caution that it seems unlikely that sufficient energy sources could exist in the European Ocean to support macrofauna, the complex sea creatures of our aquariums, for example. If life exists in Europa's oceans, it is probably quite simple and small, perhaps analogous to the most primitive single-celled organisms that have existed on Earth. The only way to find out whether life exists on Europa will be to go there. The next mission to Europa, still in its planning phases, and currently delayed because of NASA's overall budget woes, will almost certainly be an orbiter designed to determine whether the ocean exists. Subsequent missions could land on the surface. If a lander discovers any water that may have surfaced below, we can analyze it for various organic molecules like amino acids. The lander might also melt and filter a sample of surface ice, preferably a large sample since we expect the abundance of any life on Europa to be low, in search of evidence of life. We must sterilize the spacecraft to avoid transporting biology from Earth to Europe and back. 2010 movie, The Year We Make Contact. The monoliths are back and they've brought plenty of buddies. In the film 2010, a sequel to the classic 2001, humans are again prompted by some enigmatic black slabs to head for the outer solar system. An unseen race of aliens seems to be trying to make an important point about Jupiter and its moons. So we oblige them by sending yet another batch of confused astronauts on a billion-kilometer joyride. However, unlike the mission in 2001, this crotchety crew returns to Earth, bringing a few sage words of alien advice. All these worlds are yours except Europa. Attempt no landing there. What's the deal? After all, this is our solar system. So why are some unknown, unseen entities marking Europa off limits? That's like Mom forbidding you to go into a basement closet. Of course, that's the one place you'll find most interesting. And Arthur C. Clarke, the author of the novel 2010, knew that there was an interesting closet in the Jovian system. The Voyager spacecraft had shown Europa to be an ice-covered world that could have a huge liquid ocean and maybe even life. There are chlorophyll-equipped critters somewhere beneath the European ice. Alas, life in such a deep, dark habitat is a drag. So just as the humans arrive, the sophisticated aliens who built the monoliths decide to re-engineer Jupiter, turning it into a mini-sun. They do this for the benefit of the primitive life forms on Europa. The new star eventually warms its moon and converts it to something that looks like Earth during the Mesozoic era. The Europans, we presume, are destined to crawl out of their formerly ice-capped seas and find a monolith that will promote them to intelligent beings. The way our simian ancestors were improved in 2001. We lose Jupiter, but we gain a second, dimmer sun in our skies. No doubt a headache for astronomers and a source of confusion for migratory birds. But one wonders why these unseen extraterrestrials are so keen to meddle in the biological evolution of other worlds. Perhaps they want our distant descendants to have some intelligent company in the solar system. It's a wonderful thought, but someone needs to tell the space agencies that it's hands-off Europa for the next few hundred millennia. Discover it there. Indeed, in 2003, NASA deliberately ended the Galileo mission by causing the spacecraft to plunge into Jupiter's atmosphere to prevent any possibility that the spacecraft might someday crash into and contaminate Europa with hitchhiking microbes from Earth. If the results from a lander are encouraging, for example, if they show the presence of organic molecules in the ice, we could then dream and scheme about probes. Could other moons of Jupiter have life? Europa is the most likely of the Galilean moons to be habitable. However, both Ganymede and Callisto are also composed of significant amounts of water ice. Could they too have underground oceans and the possibility of life? Ganymede, the third of the 4 Galilean moons from Jupiter, is the largest moon in the solar system. Like Europa, Ganymede has a surface of hard, brittle ice. However, while Europa's impact craters have been mostly erased by other geological processes, Ganymede appears to have young and old surface regions, sometimes separated by remarkably sharp boundaries, figure 9.18. Some regions are dark and densely cratered, suggesting they look much the same today as they did billions of years ago. Other regions are light-colored with few craters, suggesting that they are geologically younger and have had their ancient craters erased. The young regions also exhibit strange grooves. The likely explanation for the younger ice regions is that they were created by water eruptions, when internal heat caused ice below the surface to melt, erupting as watery lava and then freezing. The grooves were probably made by tectonic stresses that stretched the icy crust. The idea that water sometimes erupts onto Ganymede's surface implies that partial melting must occasionally occur in the underlying ice, but could Ganymede have a full-fledged ocean like that thought to exist on Europa? The Galileo spacecraft turned its magnetometer to Ganymede just as it did to Europa and made 2 intriguing discoveries. First, Ganymede has its own intrinsic magnetic field, one generated within the Moon, which may indicate that it has a molten convecting core, somewhat like Earth's outer core. Second, the magnetometer data showed that a small part of Ganymede's magnetic field varies with Jupiter's 10-hour rotation, just like Europa's magnetic field. Again, this indicates a field produced in electrical conducting material under the surface, most likely a salty ocean. Another evidence for an underground ocean is the presence of salts on Ganymede's surface, which could be brine brought up from below. Overall, a liquid water ocean seems fairly likely to exist beneath Ganymede's frozen surface, although the case for its existence is less strong than the case for an ocean within Europa. What source of heat could keep water melted under Ganymede's surface? Because of its greater distance from Jupiter, Ganymede has much less tidal heating than Europa. However, Ganymede's larger size also means it should retain heat better than Europa. Perhaps the heat produced over time by combining tidal heating and radioactive decay has been enough to sustain a layer of subsurface liquid water. Another possibility is that Ganymede's tidal heating was greater in its youth, and it's still cooling off. While the possibility of a subsurface ocean is encouraging from the standpoint of habitability, the lesser heating on Ganymede means that the ice cover would be much thicker than on Europa. Probably at least 150 kilometers thick. This would make finding life in a subsurface ocean far more difficult, and the transport of possible nutrients from the surface considerably less efficient. In addition, the pressure in Ganymede's interior is high enough to create high-density forms of ice that likely lie beneath any liquid ocean. As a result, Ganymede probably does not have a rock-water boundary at its ocean bottom like that on either Earth or Europa. A fact that would further reduce the available energy for life. Life, if it exists on Ganymede at all, would probably be less abundant and less evolved than seems possible on Europa. It might also be so deep below the surface that we'd have little hope of gaining access. Callisto. Callisto is the farthest out of the 4 Galilean moons. Its entire surface is densely pockmarked by craters, the bright circular patches that must date back to the heavy bombardment. Other surface features are more difficult to interpret. For example, the close-up photo shows a dark, powdery substance concentrated in low-lying areas, leaving ridges and crests bright white. The dark powder may be debris left behind when ice sublimates into gas from Callisto's surface. Gravity measurements suggest that Callisto is mostly a ball of mixed ice and rock, overlaid by several hundred kilometers of water ice. Because its interior doesn't seem to be fully differentiated, we conclude that Callisto was never very warm inside, and that neither radioactive decay nor tidal heating ever heated this moon enough to melt it through. Surprisingly, however, the Galileo spacecraft found an induced magnetic field for Callisto too, suggesting, as for Europa and Ganymede, a salty subsurface ocean. What heat source could keep it liquid if a subsurface ocean exists on Callisto? Unlike the other 3 Galilean moons, Callisto doesn't participate in the orbital resonances that cause tidal heating, meaning that the warmth required to maintain a liquid ocean would almost surely have to come from radioactive decay. This meager heat source might be sufficient because of the insulating properties of thick, icy skin. In addition, the water might contain salts and ammonia that act like antifreeze to help keep it liquid at low temperatures. If Callisto really does have a deep, unseen ocean, we arrive at the astonishing possibility that 3 of Jupiter's large moons could have liquid water oceans and, perhaps, life. Energy constraints prevent these moons from having the same abundance or diversity of life as Earth. Callisto, which probably has the least energy available for life, is the least likely of the 3 moons to have life in its ocean. Nonetheless, there is the intriguing thought that any aliens coming from afar to study biology in our solar system might find much to interest them by spending time near Jupiter. Life around Saturn and beyond. Prospects for habitability and life dim considerably as we go beyond Jupiter. Although a few outer solar system moons have tidal heating, we do not find more examples quite as extreme as those of Io and Europa. The greater distance from the Sun also dampens the possibility of obtaining energy from sunlight, and cold temperatures would presumably slow any metabolic reactions. Nevertheless, the outer solar system offers some intriguing prospects for life, or at least for fascinating organic chemistry that could be a precursor to life. Could Titan have a life? The best-studied candidate for habitability beyond Jupiter is Saturn's moon Titan. The second largest moon in the solar system after Ganymede, Titan is the only solar system moon to have a substantial atmosphere. In fact, Titan's atmosphere is even thicker than Earth's. The surface pressure is about 1.5 times that on Earth, which means that if you could visit Titan, the pressure would feel comfortable even without a spacesuit. The temperature, however, would not. Here, where sunlight is nearly 100 times as weak as Earth's, the surface temperature is frigid, 180 degrees Celsius, 1, and minus 290 degrees Fahrenheit, 2. Moreover, while the atmosphere is 90% nitrogen, N22, not so different from the 77% nitrogen content of Earth's atmosphere, there is no appreciable oxygen to breathe. While Titan's low temperatures make life there seem unlikely, some intriguing chemistry occurs in this frigid, smoggy world. As a result, it was selected as a prime target for the Cassini mission that reached Saturn orbit in 2004. By 2008, Cassini had completed its original reconnaissance of the Saturn system and went into overtime, continuing to study the ringed planet and its moons. By early 2010, it had flown past Titan 66 times and had mapped much of the moon's hidden landscape. In addition, Cassini carried a probe called Huygens that parachuted to a soft landing on Titan's surface in January 2005. The results from Huygens and the ongoing observations from Cassini have revolutionized our understanding of Titan. Spectroscopic Earth observations first revealed the presence of methane in Titan's atmosphere in 1944. However, the amount of atmosphere was not immediately known, partly because methane is not the dominant gas. Nitrogen is. Because scientists originally included the hazy atmosphere when measuring Titan's size, it was once thought to be the largest moon in the solar system, which is in keeping with its name. The two Voyager spacecraft that passed by Saturn and its moons in 1980 and 1981 found that Titan's girth had been overestimated because it was puffed out by a 200-kilometer thick atmosphere. The solid part of Titan has a radius 60 kilometers smaller than that of Ganymede. Cameras aboard the Voyager spacecraft could photograph fine detail on Titan, but they saw nothing of the surface, because their vision was blocked by the opaque, reddish haze, in essence, smog. Most of the visible smog is due to chemical byproducts, formed when ultraviolet light from the sun breaks apart methane molecules. Titan's gravitational pull on the Voyager spacecraft allowed researchers to accurately determine its mass, nearly twice that of our moon. Knowing its mass and size permits us to compute its average density, nearly the same as Callisto's. This suggests that Titan comprises roughly equal volumes of rock and ice, like other large outer solar system moons. Despite the Voyager cameras being frustrated by smog, these spacecraft told us much about conditions within Titan's atmosphere. Voyager 1 was given a trajectory that allowed it to sail behind Titan, so its radio signal would pass through the smog on its way back to Earth. This ingenious experiment provided data to determine the temperature and the atmosphere's composition. The composition measurements proved especially intriguing. Besides its 90% nitrogen content, the atmosphere comprises, in order of abundance, methane, argon, and ethane. There are lesser quantities of propane, acetylene, hydrogen cyanide, and carbon dioxide. What accounts for this mixture of hydrocarbons, which reads like an oil company's product line? To begin with, once ammonia from Titan's icy interior made it into the atmosphere, energetic ultraviolet light from the sun would have broken it apart, allowing it to react to form nitrogen and hydrogen. Titan's air was primarily composed of nitrogen molecules, which were sufficiently heavy to remain stationary. The much lighter hydrogen escaped into space. When methane-1 CH42 from the interior entered the atmosphere, it too was broken apart by ultraviolet light into hydrogen, which again escaped, and the simpler compounds CH and CH2. Products of the methane breakdown then reassembled themselves into more complex hydrocarbons, especially ethane 1C, 2H, 6, 2. Eventually, this should have led to an atmosphere so saturated with ethane that a non-stop drizzle of ethane rain began to fall. So far, so good. But the fact that measurements from both Voyager and Earthbound telescopes showed that there's still lots of methane gas in the air was surprising. We might expect that it would all have been converted into other molecules long ago. This puzzle can be solved if we assume that a replenishment source, a methane reservoir, slowly feeds new gas into the atmosphere. We hypothesized that large pools of slowly evaporating methane on the surface serve as the source. Minus 180 degrees Celsius temperature should be warm enough to allow methane and ethane to be liquid. Some evaporating methane would remain in the atmosphere. Some would be converted to ethane by ultraviolet light and chemical processes. And some might even rain down. Thus, the Voyager studies suggested that Titan could have a drizzle of rain made up of methane or ethane droplets. In essence, liquid natural gas, which is largely made up of methane and ethane, and perhaps even lakes or oceans of liquid methane and ethane on the surface. Clearly, this was a world that called for further study. Given that we usually think of moons as airless worlds, like our own moon, how is it that Titan has such a thick atmosphere? In fact, the main reason why moons generally have little or no atmosphere is their small size, which results in weak gravity that is insufficient to hold on to substantial amounts of gas and little internal heat, leading to little outgassing. Titan can hold its atmosphere because of its relatively large size and extremely cold temperatures, making it less likely that gas molecules can attain escape velocity. A subtler question is why Titan has a thick atmosphere while Jupiter's moon, Ganymede, which is even larger and still quite cold, does not. There are two proposed explanations for the difference. First, recall that at Saturn's distance from the Sun, ices such as methane and ammonia should have been able to condense in the early solar system. But we expect mostly water ice at Jupiter's distance. Thus, while the outer crusts of Europa, Ganymede and Callisto are composed largely of water ice, Titan's outer layer should have substantial amounts of methane and ammonia ice. These compounds can evaporate or sublimate into gas at lower temperatures than water. Thus, if the internal temperature rose on Titan during differentiation, the methane and ammonia ice might have turned to gas, bubbled out of the crust, and built an atmosphere. A second possible reason for Titan's atmosphere is that comets and asteroids hitting the moon of Saturn are traveling at lower speeds than are those that fall onto the moons of Jupiter, both because Jupiter's stronger gravity accelerates incoming objects more, and because the Sun's attraction accelerates objects more at Jupiter's distance than at Saturn's. When such bodies slam into an atmosphere, they can blow away much of it. Impacts are more likely to have blown away Ganymede's atmosphere than Titan's. The intriguing prospect of a smoggy moon with frigid seas of liquid methane was a major incentive for launching the 2-ton Cassini-Huygens spacecraft to Saturn in 1997. After a circuitous 7-year journey that took it twice past Venus, back past Earth, and then on beyond Jupiter, with each planetary pass giving it a gravitational slingshot energy boost that was necessary because of its relatively low launch speed, Cassini reached Saturn orbit in July 2004. With infrared cameras that can see through the smoggy atmosphere, Cassini quickly gave us much clearer pictures of Titan. Our closest views of Titan came from the Huygens probe. Released from the Cassini mothership on Christmas Day 2004, the probe spent 21 days coasting toward Titan. On January 14, 2005, the probe entered Titan's smoggy atmosphere. Huygens deployed parachutes to facilitate its 2-hour descent. As the descent proceeded, the probe radioed back information about the composition and temperature of Titan's atmosphere and snapped hundreds of photos of the landscape below. The aerial views from Huygens show fantastic topographic details. Some are clearly reminiscent of coastal areas on Earth, with hills laced by branching channels that meander down to flat areas that look like rivers or lakes. However, unlike on Earth, scientists believe liquid methane and ethane, not water, are responsible for carving the channels. Huygens found no sign of flowing or pooled liquids at the time of its descent. But this is probably because Huygens landed during a dry spell, or perhaps even in a desert-like area that is only occasionally rinsed by liquids during wet seasons. Although Huygens was designed to float in case it settled onto a lake of liquid hydrocarbons, it landed on a hard surface reminiscent of a dry streambed strewn with granite-hard chunks of ice, most likely water ice. It hit the surface at about the speed of a bicycle. The parked probe continued to send back data for another hour, until the mothership sailed too far to pick up signals, and the lander's battery died. This was the first time a spacecraft from Earth landed on a moon other than ours. The Huygens probe did not find any liquids in its descent region, but the Cassini orbiter found lakes, particularly in the North Polar region of this moon. However, Cassini has ruled out the idea that Titan might be largely covered with liquid seas of methane or ethane, which some scientists had deemed likely before the spacecraft's arrival. Further analysis of Titan's atmosphere has provided new insight into its origin. In particular, aside from the argon previously identified by Voyager, the Huygens found no other noble gases of elements in the last column of the periodic table, such as krypton, xenon, or neon. These non-reactive gases are present in Earth's atmosphere, presumably due to a rain of comets billions of years ago. Once the comets smashed into our world, they trapped these relatively heavy elements. The fact that they are absent on Titan, the exception, argon, arises from the radioactive decay of potassium suggests that no gas was supplied by comets. Instead, we infer that Titan's smoggy atmosphere was outgassed from its interior. Outgassing implies some volcanism or sublimation of interior ice. But Titan's interior should not be warm enough to melt rock and drive volcanoes like those on Earth. Instead, Titan may have low-temperature volcanism where water, methane, or ammonia ices melt and cause eruptions. It's also possible for these ices to sublimate into the atmosphere as gas without melting first. Some researchers suspect that Titan has ice volcanoes, an idea that conjures up visions of icy volcanism, sometimes called cryovolcanism, which looks much like volcanism on Earth, aside from the far lower temperatures. Other researchers believe that sublimation, unlike a volcano, releases the gas. Either way, releasing methane from the interior may help explain the mystery of Titan's atmospheric methane. Perhaps the most exciting discovery to date concerns the new perspective we have gained on Titan's alien environment. Titan's landscape looks remarkably similar to Earth's, yet it is shaped by very different materials. Instead of liquid water, Titan has liquid methane and ethane. Instead of rock, Titan has ice. Instead of molten lava, Titan has a slush of water ice mixed with ammonia. Instead of dirt, Titan's surface has smog particles that rain out of the sky. Titan even has wind-sculpted dunes, found in patterns similar to those found on Earth, but possibly made of organic hydrocarbons rather than sand or snow. Evidently, the similarities in the physical processes occurring on Titan and Earth are far more important in shaping the landscapes than the two worlds, which have different compositions and temperatures. Titan is so cold that any surface water would turn into solid ice. But as we've discussed, there is strong evidence for liquid hydrocarbons on Titan. Water may not be the only life-sustaining liquid, but it has advantages over its competitors. Specifically because methane and ethane liquids are approximately 200 degrees Celsius colder than liquid water. Any life that utilizes these liquids is likely to exhibit significantly slower chemical reaction rates and, consequently, a slower metabolism than life that uses liquid water. However, Many biologists question the feasibility of such slow life. Possible exception: if life molecules have weaker chemical bonding than on Earth, reaction rates may not be as limiting. In addition, methane and ethane are far less able than water to dissolve other compounds or facilitate the chemistry that might lead to life. Consequently, the outlook for biology on Titan is bleak. It is not, however, completely hopeless. The ultraviolet light that hits Titan's atmosphere produces a wide range of organic molecules, the main contributors to the observed smog. Over billions of years, some of these compounds should have accumulated as a deep layer of organic sediment on the surface. These sediments may be the material in the dunes. Occasional impacts by comets or asteroids would provide enough heat locally to melt any water ice and create pockets of warm water that might persist for 1,000 years. While it is unclear that life could form quickly, intriguing chemistry would certainly occur. Also, if Titan really does have icy volcanoes, it could mean that there is a liquid aquifer below the surface that contains a mixture of water and ammonia. If this is true, it's possible that there could be volcanic hot springs where temperatures rise just above 0 degrees Celsius. Perhaps life could have originated in such places and gained a foothold. Another possibility suggested for powering the metabolism of simple life is chemical reactions in the upper atmosphere. These reactions produce acetylene, an energy-rich heavy compound that accumulates on the surface. The Huygens probe detected it. When acetylene reacts with oxygen, it releases much energy. Think of welding torches. On bitterly cold Titan, acetylene would react more slowly with hydrogen, releasing energy and producing methane as a waste product. The idea that Ta feeds on acetylene in this manner is only speculation, but at least a possible energy source is available. One further possibility for life on Titan is deep beneath the surface. Models of Titan's interior suggest that much like Ganymede or Callisto, it could have a liquid ocean far beneath its icy crust. However, this ocean would probably consist of a frigid ammonia in a water mixture rather than just liquid water, and the cold temperature would make life seem less likely. Even if Titan lacks biology, studying this moon will give us valuable insights into chemical processes that might have been important to the beginnings of life on the early Earth. For example, scientists would like to know whether amino acids on Titan form equally in both right and left-handed forms, or if they exist mostly in left-handed forms like those used by life on Earth. Moreover, while we frequently acknowledge that our assumptions about the conditions necessary for life may be overly conservative, we rarely explore alternative scenarios. If future missions find living things on this small and hostile world, where the liquid environment and energy sources are quite different from those on Earth today, it will most assuredly be life as we don't know it. Could other moons of Saturn have life? No other moon of Saturn is even close in size to Titan or any of Jupiter's Galilean moons. Rhea, the next largest of Saturn's moons after Titan, has less than 1/3 of Titan's diameter, and less than 1/2 the diameter of Europa, the smallest of the Galilean moons. We expect such relatively small moons to retain far less radioactive heat than larger moons, and any tidal heating should be at least slightly less effective. Nevertheless, several of Saturn's moons show evidence of past geological activity, and one, Enceladus, has surprised scientists by showing that it is geologically active today. Cassini's photos of Enceladus show a moon with some very young surface regions. The bluish tiger stripes, which are not really blue in color because the image was made with ultraviolet and infrared as well as visible light, show regions near the moon's south pole that are measurably warmer than the surrounding terrain, and close-up examination suggests that they are cracks or grooves through which material can well up from below. These regions appear to be covered by fresh ice that has solidified on the surface within no more than the past few thousand years, and possibly within just the past few decades or less. Moreover, images taken by Cassini looking at Enceladus backlit by the sun show that fountains of ice particles and water vapor are spraying from the tiger stripe regions. This is clear evidence of icy volcanism on Enceladus. Cassini's onboard cosmic dust analyzer has also found sodium compounds, such as common salt as well as simple organic compounds, in the neighborhood of this moon. This suggests that there might be a large underground ocean surrounding a rocky core. The water would dissolve a bit of the rock, thereby becoming salty. Large underground caverns could collect some of the water. This water would then slowly vaporize, producing salty grains of ice escaping through the surface's cracks, known as tiger stripes. Could the moons of Uranus or Neptune have life? As we have progressed through this chapter, we have gradually moved down the scale of potential habitability. While Europa appears likely to be habitable, Ganymede and Callisto appear less likely, and Titan and Enceladus, with their frigid temperatures, significantly limit the prospects for habitability. Nevertheless, our surprising findings make us ask whether other habitable places could still exist in our solar system. After the Galilean moons and Titan, Neptune's moon Triton is the next largest moon in our solar system. As previously discussed, Triton's backward orbit around Neptune implies its capture from its former independent orbit around the Sun. The question of how such a capture might have occurred is quite interesting. But here we are more concerned with the issue of potential habitability. Voyager 2 only took a close-up photograph of Triton once, in 1989. Its icy surface is an enigmatic mix of terrain that in some places is smooth, and in others is crinkled into patterns resembling the skin of a cantaloupe. There are few impact craters. The crater counts on Triton today, which leads scientists to estimate that its last resurfacing must have been no more than 10 to 100 million years ago. Clearly, Triton has had internal heat, possibly left over from tidal heating, that would have occurred as it was being captured into its present orbit, probably with an additional contribution from radioactive decay. Some researchers think this heat may be sufficient to occasionally cause ice volcanoes to erupt from a liquid ocean beneath the surface. The liquid would be much colder than ordinary liquid water and probably contain water mixed with ammonia, methane, or other melted ice. Perhaps the most important idea emerging from our inspection of Triton is that even a moon in Neptune's distant realms, where surface temperatures are horrifically cold, colder than minus 230 degrees Celsius, or minus 382 degrees Fahrenheit, might be geologically active and could possibly hide a liquid ocean and a refuge for life. And, given the surprise of discovering the possibility of a subsurface liquid mixture on a moon as small as Enceladus, we might find similar surprises if and when we send future spacecraft to orbit and study the satellite systems of Uranus and Neptune. Overall, while we do not yet know if any of the moons of the Jovian planets in our solar system have life, we've found at least 6 that seem potentially habitable. The lesson is clear. If similar moons are also numerous around the planets of other stars, such moons might be the most common habitats for life in the universe. Chemical energy for life. In our discussions of Europa, we discussed that simply having a heat source is insufficient to make energy available for life. To support the origin of life, there must also be a chemical pathway by which complex molecules can be made. And to support ongoing life, there must be chemical reactions that organisms can tap to fuel metabolism. Not so long ago, the only known chemical pathways for metabolism were those used by plants and animals. However, as scientists have studied microbes living in extreme environments on Earth, they have discovered many other metabolic pathways. These chemical pathways usually happen when rock meets water, like in rock layered with water underground, or when minerals react with hot water near deep-sea vents. Europa and other Jovian moons may have life that gets energy from the same chemical reactions. Therefore, We focus this chapter's case study on the process of science in action and how life can extract chemical energy. As you'll see, this topic illustrates the interdisciplinary nature of astrobiology, in which biologists discover new forms of life on Earth. Chemists and biochemists figure out how these organisms obtain energy, and planetary scientists then seek other worlds that might offer the same types of energy sources. What is the role of disequilibrium in life? From a chemical energy standpoint, the basic requirement for life is a situation in which chemicals naturally exist in an unbalanced state, which we describe as disequilibrium. The idea is similar to a scale on which you place objects on both sides to see which is heavier. If the two sides weigh the same, the scale is balanced. But if you add a little extra to one side, the scale quickly tips because it is no longer balanced. Similarly, if there is disequilibrium among chemicals, they will react just as the scale starts to tip. With a scale, the movement quickly stops because it can only move. However, the reactions can continue with chemicals if the disequilibria remain. The idea will be clearer if we go into a bit of chemistry. Any mixture of atoms and molecules can naturally undergo chemical reactions that may rearrange the atoms to form or break chemical bonds. Left to themselves, however, chemical reactions will ultimately come to an equilibrium that represents a balance between the reacting atoms and molecules and the product atoms and molecules. For example, molecular hydrogen and oxygen can react together to make water. We can write this chemical reaction as H2 plus 1, O2 dot H2O. The double arrow indicates that the reaction can proceed in both directions, and the one in front of the O2 indicates that the reaction requires only half as many oxygen molecules as hydrogen molecules. If we begin by mixing hydrogen and oxygen, at first the reaction will proceed only toward making water molecules since no water is present initially. Eventually, the reaction will proceed at equal rates in both directions, and we will have chemical equilibrium. Hydrogen and oxygen will be converted to water almost always, but not always. The relative amounts of hydrogen, oxygen, and water at equilibrium depend on the external circumstances, such as pressure, temperature, and other chemicals. For example, the reaction between H2 and O2 needs a push to get it started. This push might come from lighting a match in a room filled with these two gases. The energy from the match gets the reaction started. As H2 and O2 combine to form H2O, additional energy can trigger more molecules to combine. This sequence can occur rapidly, and the energy released can cause an explosion. Now, imagine that the reaction between hydrogen and oxygen occurs in a small flask inside a large room and has reached equilibrium at the room's temperature. Suppose we do something suddenly that disturbs the equilibrium, such as adding excess hydrogen and oxygen molecules. Because the excess hydrogen and oxygen mean that the reaction is no longer in equilibrium, we have created a state of disequilibrium. The water formation rate will accelerate due to this disequilibrium until we restore the equilibrium. Note that once we force the chemicals into disequilibrium, the rest of the process is completely natural. The reaction rate changes automatically in such a way as to bring the relative amounts of hydrogen, oxygen, and water back to their equilibrium values. Under the right circumstances, these reactions returning to equilibrium can release chemical energy that life might use to fuel metabolism. No one is adding chemicals to the mixture of life. So the key to making chemical energy available for life lies in having some natural set of circumstances that can create and maintain a state of disequilibrium. In that case, the ongoing disequilibrium means that the reactions always try to return to equilibrium, offering a continuous chemical energy source. Natural processes that maintain chemical disequilibrium are quite common on Earth and may exist to some extent in any geologically active world. For example, chemical disequilibrium inevitably exists near deep-sea volcanic vents, because mixing between the high-temperature vent water and the surrounding low-temperature ocean water creates conditions where minerals and water will undergo chemical reactions. Because the vents continually release hot water, the disequilibrium can be maintained for long periods. Another place where we find ongoing disequilibrium is at interfaces between rock and water. The rock and water will naturally undergo chemical reactions, and as long as there is a supply of water that continuously circulates and comes in contact with the rock, the reactions will remain out of equilibrium. Thus, chemical disequilibrium can provide ongoing energy to create complex molecules in both deep-sea vents and rock-water interfaces. This energy can also string complex molecules together into complicated structures, a process that may have been important to the origin of life, or support the metabolism of living organisms. What types of chemical reactions supply energy for life? Chemical disequilibrium offers the potential to provide chemical energy for life, but realizing this potential requires chemical reactions that life can actually use. A particular class of chemical reactions turns out to be especially important for life on Earth. Reactions called redox reactions. In redox reactions, the reacting atoms or molecules trade or rearrange their electric charge by moving electrons around. Let's consider again what happens when hydrogen and oxygen combine to make water. Viewed on a molecular level, the reaction occurs in two steps. First, a hydrogen molecule decomposes into two protons, hydrogen nuclei, and two electrons. H+ represents a single proton which is positively charged, and E- represents a single negatively charged electron. Next, the two protons and two electrons combine with an oxygen atom, half of an oxygen molecule, to make a water molecule. When we view water production as a redox reaction, it effectively transfers electrons from hydrogen to oxygen. Because hydrogen gives up the electrons, we say it is the electron donor for the overall reaction. Because oxygen takes on the electrons, it acts as the electron acceptor. When oxygen accepts electrons, its electrical charge goes down because electrons are negatively charged. This is what the first three letters of redox mean: lowering electrical charge. The charge of the hydrogen is increased, but because this increase occurs as the result of action by oxygen, we say that the hydrogen has become oxidized. In fact, oxygen is so efficient at grabbing electrons from other chemicals, atoms or molecules, that chemists have used the term oxidation to describe losing electrons in general, even when the electrons are lost to something besides oxygen. Thus, the overall process of making water from hydrogen and oxygen is called a redox reaction, because the oxygen gets reduced while the hydrogen oxidizes. A redox reaction always involves the transfer of one or more electrons from an electron donor, which becomes oxidized, to an electron acceptor, which becomes reduced. This energy-rich transfer can drive other chemical reactions, including the biochemical reactions of life. Most of the key energy-generating chemicals life uses on Earth are redox reactions. For example, the basic process of aerobic respiration in animals involves combining a sugar acquired by eating, such as glucose, C6H12O6, with oxygen acquired by breathing. The reaction makes carbon dioxide and water and releases energy in the process. Many energy-making processes in cells involve chains of redox reactions, which are also known as electron transport chains. This is because a chain of redox reactions means a chain of electron transfers. In photosynthesis, for example, the chain begins when chlorophyll absorbs sunlight. The energy from the sunlight creates disequilibrium in the cell, which then offers power that the cell utilizes through a chain of redox reactions. Possible redox reactions for other worlds. Redox reactions are especially important when considering the prospects for life in extreme environments, either on Earth or in other worlds. Many Earth organisms use fairly simple redox reactions as their primary energy source. For example, bacteria known as Thiobacillus ferrooxidans, which can thrive in highly acidic conditions such as in mine tailings, obtain energy by oxidizing iron. As a result of the understanding of this chemistry gained by studying life on Earth, we now have reason to think that life could exist on many other worlds. In particular, any geologically active world with liquid water may have places where chemical disequilibrium persists for long periods, such as near underwater volcanic vents or anywhere where rock and water come into contact. At these places, redox reactions can provide energy that could power biochemical reactions that might ultimately lead to life, and that could support life once it arises. That is why places such as underground pockets of liquid